Okay, so we're going to start lesson 6.2. 6.2 is a sort of, it starts with the review of binomial experiments. And we learned that binomial distributions, which are the probabilities associated, that those distributions are often bell-shaped. And that actually leads us toward being able to create a theory for sample proportions, which are very closely related to binomial experiments. And it turns out that sample proportions have normal distributions. Okay, so let me go ahead and we're going to start with just a review of binomial experiments, and then we'll show that we can actually compute these probabilities differently from what we did before. So section 6.2, previously we learned about binomial experiments. Binomial experiments consist of n independent trials where each trial has two outcomes, success and failure. The probability of success is little p. The probability of failure is q, that's 1 minus little p, and x is the number of successes. Okay, the probability of x successes is denoted p of x, and the formula for computing the probability of x successes is this one. P of x is n choose x, p to the x, q to the n minus x. Okay, so we're going to start a little example, supposing that the president has a 45% approval rate and that you've surveyed 10 people. If x represents the number of presidential approvals, compute the probability distribution below. And we're going to identify n and p first. So it says that there's 10 people. Those are the trials. So n is 10. Little p is the probability of success, and a success is an approval. If the president has a 45% approval rate, then the probability of getting an approval is 45%, 0.45. Okay. Now, if we wanted to compute one of these probabilities, let's do one of these in the table that's left blank. So the probability that x is 4 works. I guess we should do q, which is 1 minus p. So q is going to be 0.55. If p is 4.45, remember those are complements. Okay, and then the probability that x is 4 well, the formula again is n choose x, p to the x, and q to the n minus x. All right, we can fill in some of this. N is 10. 10 choose 4. Don't know what it is. And then p will be 0.45 to the x, which is 4. And q is 0.55 to the n minus x, that'll be 10 minus 4. Like that. All right, I'm gonna move this a little bit again. And we just need to compute it now. So I think the best way to do that is using Desmos. So I'm going to pop over to Desmos real quick. Let me open up a new window in my browser. And we'll go to desmos.com. Okay, and just to remind you, there's a clever thing in Desmos that does the n choose x. They actually call it NCR, like that. And you put in the 10, which is n, and the 4, which is x, and it says it's 210. So we'll put in 210 for the 10 choose 4. in the notes. But I think what I want to do here is do all the computations. So I think what we'll do is let's go ahead and do the 210 times the p to the x. P was 0.45 to the x. That would be to the fourth. And then pop out of that exponent, and again times q, which is 0.55. And then that's to the 10 minus 4, which is 6. And you can see the answer there is a 2384, I guess. Okay, so I think I'll go ahead and fill in what we've got here. So I'm going to go back to my iPad. Okay, so the 10 choose 4, that's the 210 times 0.45 to the fourth times 0.55, that was to the 10 minus 4, which is 6. And I think that came out in Desmos to 0.2384. And so that's the probability of getting 4 successes here. And I'll squeeze that in. There's a bunch more to do here. So I'm going to pop back over to Desmos and show you a real clever way to get this sort of automatically just by giving it the formula. So I'm going to go back to Desmos. Okay. And I think I'll just delete everything I did already. And this time what we're going to do is we're going to tell it that n is 10. And I'm going to use a capital X because X isn't supposed to have values in Desmos. Lowercase x is used for graphing, but capital X can have the value. So, I'm not going to give X a value. I think what I'm going to do is just type in what P is. P is 0.45. And then on the next line, I'll say that Q is 1 minus P. Like that, which is 0.55, it says. I think that's all we need to do the formula. So the formula for the probability is N, C, they use an R, and then my inputs will be N, which is 10 up above, and X, which is going to be my variable. Actually, I think I can use the lowercase x. Let's see what happens. It's going to try and graph it. Ooh, I don't know if that'll work or not. And then times. Yeah, no, that's not going to work. Use a capital X. Okay, and then this will be times. There'll be a mistake here. Okay, so times it's p to the x, so little p to the capital X, and then times little q to the little n minus capital X. Oops. That needs to go up in there in the superscript, the exponent. So I'll use parentheses. N minus capital X will do the trick. And then I'm going to add a slider for X and let X be all the values I need. So I want X. Let me change the settings on this. I want X to go from 0 to 10 successes in increments of 1. Okay, and I think now I can let X slide, and as I do let X slide, it's not working. I think I made a mistake. Let me fix that. 0 to 10. Somehow I screwed that up. Okay, so is it going to work now? Yeah. So here I let the slider slide, and I don't know if you can see, but the probability for P of X changes as I slide this. Okay, so I'm going to start with x equals 0, and you can see the probability is 0.0025. I'm going to copy that into the handout. Okay. There's also a blank where x is 7. So I'm going to slide this up to where x is 7 there. And the probability is 0.0746. So I'm copying that into the lesson. Like that. Okay, if you slide it up to 8, you'll see it says 0.02288, so it would say 0.0229, which is exactly what the probability is that's given already in the lesson. But 9 is blank, so I have to slide this up to a 9, and it's 0.00416, which we'll call 0.0042. Okay, so now I'll go on back. So that's computing the whole probability distribution. I'm going to go back to my iPad here. Okay, and now you can see the whole probability distribution entered in here. Okay, so you get all these probabilities built in, and what we want to show is how this comes out as a bell-shaped distribution. I think we've done problems this big before, but honestly, I can't remember. We want to show this is bell-shaped and show how we can get these probabilities with a regular smooth bell curve and have them come out almost the same. Okay, so I want to show you, we're going to kind of walk through this. If I'm going to use the normal distribution, I'll need a mean and a standard deviation. So we gave the mean and the standard deviation for the binomial distribution here. The mean is NP, and the standard deviation is the square root of NPQ. So let's go ahead and do that. On this one, the mean is NP, which is, let me just put the formula in, but N was 10, P was 0.45. So the mean is 4.5 on this distribution, and you should see that 4.5 is right in the center of all the probability. Standard deviation, square root of NPQ. Okay, so that's the square root of 10 times 0.45 times 0.55. Okay, and then let's see if we can agree on that. Don't forget to take the square root. That people taking one of the most common problems that mistakes people make on problems that involve square roots is just forgetting the square root. And I think that probably includes me. Now let's do a few places after the desk, maybe 3 or 4 places, only because I'm going to try and do something later that'll I'll benefit from a little more precision this time. So anybody, can we do 4 places? All right, well, I got 1.5732. I hope that's what you got.
I'm doing it right now.
It's okay. Yeah, just so if you get the same thing, that would be awesome. Okay. Now, just to let you know, again, we've got all the probabilities up here. So there's nothing really unknown about this problem, but it's asking for the probability of getting from a 4 to a 6, okay? And that's not using any tricks. We're just going to use the probabilities above. So the dog. Probability of getting a 4 or a 5 or a 6. These are mutually exclusive, which means that you can just add these probabilities up. So the probability of 4 plus the probability of a 5 plus the probability of getting a 6. Okay, and so these probabilities are above. The 4 is 0.2384. Plus for 5, it was 0.2340. For 6, it's 0.1596. And we need to add those up. So if you don't mind, take a sec and let's see if we can agree on this. Okay, anybody?
0.632.
Yeah, and I'm going to put the 0 after it, 6320. The computer doesn't, or your calculator doesn't show trailing zeros, but we actually know this digit. It's a 0, so I'm going to go ahead and record it so that it's clear that I have 4 places after the decimal. Okay, the calculator just drops zeros at the end of numbers unless you have a mode that allows you to keep it. Now this is where it's going to get a little tricky because I want to do a graph of all these probabilities. So right now I'm getting ready to draw a bunch of rectangles. And I'm trying to get my iPad to give me one good rectangle. There's a good one. Okay, so I just need to get the heights straight here. But this first one's going to be really small. So let me see here. The first one has a height of 0.0025. And the last one's basically the same. So I'm going to paste in. Actually, I'll paste that first one in. And 0.00 is just practically 0. So this will be almost invisible. Maybe like that. Okay, the second one is a height of 0.0207, so that's easy. I can just come down to just above the 0.02 here, like that. Okay, next one has a height of 0.0763, almost 0.08. Here, I think. Okay, the fourth one.
So we went down several hills right now. Like, how do you even determine?
What? I didn't understand what you said. Who was that? I have this funny feeling that wasn't for me.
It wasn't. I'm so sorry.
Were you talking to me?
No, I wasn't. I'm sorry.
How dare you? Cool. Okay, so well, I lost where I'm on 3. So for 3, it was 0.1665. Let's hear for Zoom. 1665. It looks good. Okay, and then I'm on 4 now, which is 02384. Okay, so let's do that one. Okay, and then 5 is 2340, almost the same. Just a little shorter on that one. I'm gonna have a little trouble pulling this off. Okay, so that was 5. Sorry, I'm going so slow. 6 is almost 0.16. Okay, 7.0746. Okay, 8 is 0229. That should be easy enough. Something like that. So 9 is 0.0042. That's really low. See if I can get that in there. 0.004 is going to be about that high, I think. And then the last one will be super small. I'm just going to copy the first one and paste it over like this. So now it's not perfectly symmetric, I think is one thing we want to get out of this. And remember, what I had said was I'd like to use a bell curve, a smooth normal distribution, to show that I can get areas that are almost the same as the areas of these rectangles. Okay, and I only need to be within a percentage point, really, and I'll be happy. Let me go ahead. I want to superimpose a bell curve over this just to kind of show you where we're going. Okay, and the mean, remember, was 4.5. So right here in the middle, as it looks like it should be, is the mean, 4.5. Okay, so in terms of shape, this is a rough histogram or a rough bell shape, forgive me. Okay. We have the mean, we have the shape, we have the standard deviation. So that's center, shape, and spread. Those are the 3 numbers that allow us to determine probabilities, or the 3 ideas: center, shape, and spread. Now it says use a normal curve to compute the same probability. So that's crazy. I'm going to make this a different color so it's more apparent. Interesting. Okay. I'm going to remove. Okay, just give me a second, you guys. Oh, I didn't mean to do that. I just removed the fill. because I decided it, or the fill on the rectangles, because I decided it was making it hard. Okay, so what I want to do is determine the same probability. We did a probability that X was between 4 and 6 up here. Okay, and I want to do the same thing with this diagram and the smooth bell curve. So I'm going to shade just from 4 to 6, but the rectangles actually start at 3.5. And if I go up to 6, that will stop at 6.5. Okay. Okay, so first of all, let's mark off the start and end point. Remember, the probability is the area. And to get the probability right, you have to get the area right. And area is width times height. You better get the width right. It doesn't go from 3 to 6. It goes from 4 to 6. It goes from 3.5 to 6.5. Okay. So if you take this original question, what's the probability of getting between 4 and 6 approvals? Let's go ahead and put it down here. Probability that Z is between 4 and 6 approvals. Okay, turn some light on, it's too dark. Okay, so, and I don't mean Z, I mean X, which is the number of successes in the binomial experiment. We will convert to Z-scores, but first I want to be explicit and say, all right, well, for X to be equal to 4, 5, or 6 on the number line, that means that X is going to go from 3.5 to 6.5. Okay, so this step is called a continuity correction. Okay, so what we do when we use a smooth distribution like this to do discrete probabilities, that's kind of doing it wrong. You're starting with a good discrete variable that has its own probability distribution, and you're treating it as if it was a continuous variable. If you're going to do that, you have to recognize that discrete variables have kind of thickness to them. You know, where when I say X equals 4, that really means 3.5 to 4.5. So I have to give it that thickness before I use a continuous probability curve to determine the probability. Okay. So is there any question about that weird step that I just did? The rest is, this is absolutely straightforward. Okay, we would just say, okay, so let's convert to Z-scores. Looks bell-shaped, so I'm going to go ahead and put a Z-score here. Okay, and then do Z-scores of the endpoints. So if X is 3.5, Z is always X minus mu over sigma. And we're going to have to go back and remind ourselves that the mean up here is 4.5 and the standard deviation is 1.5732. I'll just indicate that down here. So the mean was 4.5 and the standard deviation, what did I say? 1.7532? Yeah, oh, 1.5732. Like that. And then the X is 3.5. So you just do 3.5 minus 4.5 over 1.5732. And see what you get there.
I got negative 0.636.
Good. And what we're gonna do is round it to the nearest hundredth. Again, because I'm gonna use table A1. So let's write negative 0.64. Okay, so that means the lower limit on X gets changed to a lower limit of negative 0.64 on Z. Now we will need an upper limit. So the upper limit on X is 6.5. So let's convert that to an upper limit on Z. Okay, so same thing, but here you're putting a 6.5 in. So let me know if you get it, anybody?
$1.27.
Yeah, so 1.27, thank you so much. Okay, so that's the upper limit for Z in the probability. Okay, so 1.27. Okay, so just again, we're using a continuous distribution for a discrete variable. That's not really going to give exactly the right answer because this is not a continuous variable. The number of people who say, yes, I approve of the president is a whole number. Continuous distributions are for fraction, any kind of number, which, just a real number. Okay, any number on the number line. So we're kind of bending the rules a little bit, but the question will be, well, does it work? Okay, so I think what I want to do now is just try and draw table A1. Okay, so we'll do the negative 0.64 for Z. So you go down to negative 0.6 and over to 0.04. And then on the other one, we'll go down to 1.2 and over to 0.07. And I don't know where if I have a copy of this here somewhere. Uh-oh. So you're going to have to go back to the prior table A1. I think I've got a copy here. Oops. Okay, so sorry about that. Popping all over the place. So here's a table A1. Okay, so the first one was negative 0.64, so we'll do that. So for that one, hopefully you're seeing a 0.2611 here. Okay, that's for the negative 0.64. So I'll just pop that back in. I already don't remember what it was. Does anyone remember what it was? Was it 2611? 2611. Okay, and then let's look up the 1.27 now. Okay, so that looks like 0.8980. Any questions? So again, this table is at the back of the chapter 5 notes. Okay, so let me slide that back here. Oh God, I forgot it already. That's how bad it is. Okay, it was not 8980. Okay, and this is probability of getting between these two. So is this, what do we do with these two numbers, these two areas? Anybody?
It was large minus smaller area.
Yeah, good. So we want to do the 0.8980 minus the 0.2611. Okay. So anybody just shout it out when you get it.
Point 6369.
Good. So 0.6369, that's using the normal distribution. The actual more accurate answer is 0.632. So this one that we did is exact to 4 places. Okay. The other, because it's a binomial experiment, right? And if you're going to be doing a binomial experiment and you want the right probabilities, then they're going to come from the binomial formula, which is what we had done back here. Okay, and we filled out all the probabilities with the binomial formula. But the bell curve is a smooth distribution, completely different nature of a variable. And yet, because this distribution is bell-shaped, we are able to get a probability of about 63%. Now, again, the right probability is 63.2 here. Okay, that's exact to 4 places. This is 63.9, which is, this is approximate. I'll just say approximately correct. Okay, this one comes out, if you want, you can say it's 63.7% ish, where the other one was 63.2%. Okay, now, if you just kind of think about the math involved here, to get this probability for a range of values, there's a lot of computation. And I don't know if you can appreciate it as much because we didn't do the whole table, but there's a lot of computations involved here that went in to computing the distribution. And in general, we're not going to do just 10 people in a survey. The kind of the base amount that most polling organizations do is 1,000 people and more. If they go less, they hopefully don't do too much less than 1,000. But the point is that we're going to need to basically do these things we call p-values in the homework discussion today. And the p-value is the probability of getting, let's say, 700 or more affirmative responses to whatever your question is. 700 out of 1,000, that's a lot of probabilities that are all going to be rounded and then all added up with rounding error compounded hundreds of times to give an answer that's probably not very good. So even though you're doing it the right way, you're rounding so much and doing so much more computation that it's just in the end, it sort of works against itself. So doing it the right way ends up giving just a lot of trouble. And if you can get the answer to within, half of a decimal point, which again, we had 63.2. If you can get the answer to within a half a decimal point, I mean, statistics is all about approximating stuff. Nothing's ever perfect. So half of a percentage point is pretty darn good, and it'll be good enough. Okay, so the bottom line is if you think about how much computation went into this, basically 2 z-scores, yeah, and then a probability, rather than a whole bunch of probabilities that get added up. So overall, this method where you're finding all these probabilities individually and then adding them up is more computational than just finding 2 z-scores and then determining the area between them. Okay, so this normal curve to approximate a binomial distribution probability is what we're going to be doing for now on. And every time we work with with categorical data, that's effectively a binomial experiment. And we just use the normal curve to find probabilities on these. And you'll see that probability will go straight toward the margin of error for a percentage as we get to it. Okay. So now what I wanted to do is to do a little demonstration to show you that sometimes binomial distributions, I mean, this distribution came out pretty neat and symmetric, but in general, they don't always come out symmetric. So I want you guys to see basically a real quick binomial distribution applet here. And I wonder if I'll get in trouble by asking Desmos to do this. I'm going to try it and see what happens. This time, nah, I don't have it. I have no confidence. So I'm just going to Google. Let me share my screen here. Okay, I was going to do this in Excel, but I want to go faster than that. So real quickly, I'm going to just do a binomial distribution calculator and see if I get something good here. Let's see what this one is. No, I don't see a graph there, so I'm not interested in that one. What about this one? Ooh, I like the looks of this. So if I put in, I don't know if it's going to do a graph or not, but if I put in 10 and probability is 0.45 and it does a graph. Ooh, nice. I'm not going to put in a value for X. So let me just show you this real quick, you guys. I thought I was sharing my screen and I feel rather stupid right now. FYI. Okay, now you're looking at my screen. Okay, so all I did, I don't know if you can see what I Googled. I Googled a binomial distribution calculator here. And the first one was not, it did the probabilities, but it didn't have a nice graph in it. And so the second one was this one. And if you just put in that n is 10, the way we had done, and p is 0.45, which is what we did, I just tabbed over to X and it already did the graph, and you can see that nice bell shape. What I want to get out of this is that there are situations where this doesn't look symmetric. You have to remember that n times p is the mean right now. So the mean on this one is 4.5. But if p turns out to be like 0.1, uh-oh, I did it wrong. So if I put in a 0.1 for p, you should see a non-symmetric graph here. That's not bell-shaped. So there are conditions that we have to establish for when a binomial distribution is bell-shaped. Just even with p equal to 0.1, the problem is that the mean is n times p. So 10 times 0.1, the mean is 1. And of course, that's the highest bar in the distribution at the mean. So the mean is too close to 0. And that's why the distribution is not symmetric. If I make the p 0.9, then the mean is now 10 times 0.9, which is 9. And now you can see the highest bar is at 9. And so this distribution is also not symmetric. This one's skewed to the left. The previous one was skewed to the right. Okay. So if we're going to use a bell curve to approximate a binomial distribution, we need the mean not to be too far to the right or too far to the left. Again, if I make p 0.1, you end up with a mean that's too close to 0. Okay. And so one way you can solve this is you can't control what the population proportion is, which is what p is. But you can increase your sample size. So notice if I make the sample size 100, then the distribution becomes symmetric again, because now the mean is n times p, which is 10. And it turns out if the mean is at least 10 in length, that's going to be our rule. And the reason why we use that rule is because if the mean is at least 10 in length, then you get a tail on the left that's 10. And that's long enough for it to sort of zero out and make a sort of nice left tail. Okay. Also, the right tail needs to be at least 10 in length. So watch what happens with p equal to 0.9. Again, I have a little bit of a skew to the left now, but the right tail does vanish, and it vanishes on both sides. So it turns out because the mean here is 100 times 0.9, which is 90, because the mean is 90, the length of the right tail from 90 to 100 is 10. So as long as the left tail and the right tail are 10 in length, we'll say that this is close enough to a nice bell-shaped distribution. Okay, any questions about that? So we're going to put that in the notes real quick. So I'm going to pop back over to the notes. And by the way, the bigger n is, the more bell-shaped this will look. So if I make n 1,000, once again, I think it glitched. Or maybe it doesn't allow it to go that high. I don't know. I'm going to refresh the page. Reload it. Okay, so I'm going to try to make n 1,000. And once again, make p 0.9, so it's 90%, and then say a little prayer. No, it's glitched. I don't know. Apparently it doesn't like it. What if I did 500? And then, there we go. So if you make your n big enough, you get real nice bell curves out of this. And even if p is 0.1, again, really symmetric, looks good. Okay, so again, we want that left tail to be at least 10 in length and the right tail to be 10. Okay, so let me pop back over to the notes. I'm having a little trouble here. Oh, there it goes. Okay, so let me just kind of do this real quickly here. It says your instructor used a computer applet to demonstrate the shape of normal distributions under, binomial distributions under different conditions. Pay attention, your job is to learn when a binomial distribution is approximately normal. First of all, we saw that some of these don't look normal. So the question is the normal distribution always a good approximation of the binomial? And the answer is no. Sometimes the binomial distribution is skewed. Okay, so I think I can sort of do this over here. What I want to do is sort of draw a histogram with the bell curve on top of it, and just kind of do a little algebra to show you how the rule works. So let's say this is a binomial experiment. And the lowest value, and I'll put X down for this horizontal line here. So that's the X number line, the number of successes. The lowest value of X is 0 successes. And out of N trials, the most successes is N, okay? The mean number of success is mu, which is NP. Okay, so let me squeeze that over a bit. So the mean is just N times P in a binomial experiment. Now the rule that I mentioned to you is that the left tail has to be at least 10. So the left tail is this distance. From 0 to NP, the distance is NP, okay? That has to be at least 10, and N times P is the length of the left tail. Okay, and I say at least, that means greater than or equal to 10. Okay, now there's also a right tail that needs to be at least 10 in length. That's this distance. Okay, now to find the length of the right tail, you have to do the distance from NP to N, and to get the distance between two numbers, you just subtract. So this is N minus NP to find the distance between N and NP, where the mean is. Okay. This is N. If you factor it out, you get N times 1 minus P. But 1 minus P is Q. So this is just NQ, and NQ is the length of the right tail. This also has to be at least 10 in length. Okay, so again, NQ is the length of the right tail. Okay, so this is where the following rule comes from. We need the left tail, oops, which is NP. Let me say left tail length, that'll be a little more clear. And right tail length which is NQ, to both be at least 10. That is, NP has to be at least 10, and NQ has to be at least 10. And we've just learned, through a lot of experience, that as long as those two facts are satisfied, that you can use a normal curve to approximate a binomial probability. Okay. So here, let's do a little bit more. Now we've established all the rules for normality for the binomial distribution. Our goal is now to move into proportions from samples. Whenever we work with categorical data, the summary statistic is always just a proportion, like, this percentage of people approve of the president. So we're studying proportions now from samples, and we'd like to compute a margin of error for a proportion. Okay, so let's go ahead and just read this real quick. It says, suppose you actually conduct this experiment. That is, remember, you're picking 10 people randomly that I assume are like adults, and you're just trying to determine how many of them approved of the president. So it looks like we've picked a sample of size 10, and we observe 6 approvals. And so the question is, what proportion of the sample approves of the president? So the proportion is 6 over 10, which is 0.60 or 60%. Okay, now that proportion is going to be called a sample proportion. So I'm going to write in front sample proportion, and this is going to be called P with a hat on it. Okay, and just to remind you that the population proportion is the overall approval rating for everyone. So that was 45%. That was given in the very beginning. So the population proportion is P, which is 0.45. But samples won't always be the same as populations. Okay, you can have 45% of a population approving, and at the same time have 60% of a sample that approves. Okay, and therefore we expect these sample statistics to contain some error if they're used to estimate something for the whole population. Okay, now they want us to write this proportion as a percentage, so 60% is what we've got here. Okay, but that statistic has error. So then they say, what's the probability that such a proportion is observed? So the proportion is 0.60, or 6 out of 10. Required 6 successes, and the probability, let's just say with a probability of, I just have to go back here, 6 successes way back. Here's the probability of 6 successes. It was 0.1596. Okay, so we'll say with a probability of 0.1596. And I'm just going to paste this in down here. And actually, I think I'll add another column to the table. Looks like there's a mistake, a reference problem on this question here below. But let's take these one at a time. So first thing I want to do is put in the values of X. X was the number of approvals, just to remind you. So I'm going to just sort of extend this table a bit. Okay, what all I wanted to do here was put a column for X. So X was the number of successes in 10 trials. So that could be 0, 1, 2, 3, 4, etc. 5, 6, 7, 8, 9, or 10 successes. Okay. And then P hat is X over N. Just a reminder, P hat is X over N. That's the sample proportion. Okay, so if you get 0 successes, that's a proportion of 0 out of 10. 1 success is 1 out of 10. And if you do the math, 1 success is 0.1. 1 out of 10, 0.1. So I'll write 0.10. Okay. For 2 successes, this is 2 out of 10, which is 20%, 0.20. 3 successes is 30%, 0.30. 4 is 4.40, 5 is 0.50, and so on. Okay. Now, well, those are the proportions, and every proportion has a probability related to it that came from the previous table. So unfortunately, I'm going to have to be sliding back and forth. I wonder what I really want to do is a screen capture, but I think that'll be too hard. So I'm going to slide. I think I know what I'll do. I have an idea. So here are the probabilities. Let me, I'm going to copy that on my laptop and open that up. And then I'll copy these probabilities down here. Okay, so for 0 successes, the probability was 0.0025. We got 1 success with it, which was 10% success. For 2 successes, it was 0.0763. 3 successes, 0.1665. 4 was 0.2384. 5 we've got. 6 was 0.1956. 7 was 0.0746. We got 8, 9 is 0.0042. Okay. Now, it seems like the probabilities are the same. So the histogram is going to have the same shape. And if I almost feel like I could copy it over, but I don't know if the heights will be right if I do. But I'm going to try and just copy those bars over from the last histogram. So let me just show you. I'm going back to this histogram that we drew. Boy, is that the same height? Looks similar. Let's see. So I'm just going to copy all these probabilities over because they're the same. And then I'll adjust the heights if I need to. I'm sure the whole thing is going to be wrong. It's the same probabilities, and I kind of want that emphasized, so I don't mind just pasting this over, but I'll probably have to do a little bit of correction here as I go. Okay, so all I'm doing, you guys, just to make sure it's clear, is I'm just doing a histogram for these proportions, these sample proportions. Okay, so the only difference, the only thing that's really changed with the histogram is I'm using P hat down here, which is a proportion from the sample. Okay. So real quickly, I'm just going to go through and clean up mine. I know you're doing your own histogram here. So the heights are up there. I'm going to fix the widths of my bars so that they fit this graph here. All right, so that's pretty good. Same probabilities as these. So in terms of shape, it's still bell-shaped. So I think we can just, but you see, again, this is p hat, a distribution of sample proportions. P hat is x over n. So basically every value of x has been divided by n here. Okay, in terms of shape, it's still a bell shape. Okay, same as before. This will be bell shaped, and I'll say, and the rule will continue to be what I said before. NP will need to be at least 10 for a bell shaped, and NQ will need to be at least 10. That's actually not satisfied by this example, even though the distribution is bell shaped and pretty symmetric. Okay. Okay. So they want, this is a distribution of sample proportions, p hat. And what I need is a mean and a standard deviation. I can see the shape is bell shaped. Okay. And everything's about center, shape, and spread. So the shape is a bell shape, but you can see the center here is different from the mean before. Before the mean was 4.5. Now the mean looks like it's 0.45. Okay. And so I think what I want to do is just show you how the mean works. Just to remind you how, I'll just show you the rules for expected value. So real quickly here, I think I'll do it over here. The expected value, these are just rules. Right now, all I need is the expected value of kx is k times the expected value of x. So I'm going to keep that handy. Okay. The variance of kx we showed, and k could be any number at all. It turns out to be k squared times the variance of x. Okay, so if I do the expected value of p hat, just to remind you, p hat is x over n. So this is the expected value of the variable x divided by the sample size. That's what p hat is. Okay, but n is just your sample size. It's a constant. So n is one, sorry, the expected value of x over n, you can bring the n, the 1 over n out and just leave it as the expected value of x. Now, the expected value of x is the mean from the binomial experiment. So if you go back to the binomial experiment that we started with, the mean is right here. It's n times p. That's the expected value of x. Okay. While I'm looking at the standard deviation is the square root of npq, which means the variance of x is sigma squared. So that'll just be npq without the square root. Okay, so we'll need that in a second. Variance is npq. Now, if we go back down here, we said the expected value of x is n times p. So we would do, this is 1 over n times the expected value, which is np. So this is just p. Population proportion. Okay, so let me reiterate what this is saying is that sample proportions, p hat, sample proportion has an expected value that is the population proportion. So sample proportions estimate the population proportion. You get all different estimates with different probabilities. Here are the probabilities for all the sample proportions. They vary, but the mean of the sample proportions is the population proportion, which is p. So in the middle of this distribution is the population proportion. In the very beginning, it said that the president has a 45% approval rating. That's the population proportion. And it is the center of all the sample proportions. So every sample is going to give a different proportion. It's only 10%. Sorry, it's only 10 people. So you're either going to get 0%, 10%, 20%, 30%, and so on, as you see with the graph. But the population proportion is none of those. The population proportion is 45%. It turns out it fits perfectly in the center of the distribution, right between all the sample proportions, and is a perfect balancing point for that distribution. Okay, any questions about that? So down here, this is the mean of sample proportions. Okay, we do a mu with a little p hat next to it. Okay, so the mean of the sample proportions is p. That's the population proportion. Okay. So again, just remember there are many sample proportions all arrayed along this number line. All the sample proportions are listed in this list. There are many sample proportions. Okay, but there's only one population proportion, and it turns out to be the mean of the sample proportions. Okay, any questions? So I have shape, I have center, which is always the mean. The only thing that's left is spread. That'll be the standard deviation. Okay, so I'm going to go ahead and show you the variance of p hat up here. So variance, which is the square of standard deviation, variance of p hat is the variance of what p hat is. P hat is x over n, like that. Now 1 over n is just a constant, just like k is a constant over here. it comes out as a k squared times the variance. Okay, so here I'm going to write, oh, that's 1 over n squared times the variance of x. Okay, the variance of x from the binomial experiment. So then I can slide back and remind myself, oh, the binomial experiment is where the variance is sigma squared. That'll just be NPQ. So if I come back down, I can change this to 1 over n squared times the variance, which is NPQ. And so if you cancel, you can see that an n is going to cancel one of the n's in the denominator. So this will be PQ over n for the variance of a sample proportion of all the different sample proportions here. PQ over n, okay? And the standard deviation is the square root of variance. So down here, I'm down at this part down here. So I am computing the standard deviation of sample proportions. I think I'll put that down here, standard deviation of sample proportions. Okay, this would be the square root of the variance of sample proportions. Okay, but that is the square root of what we derived up above, square root of PQ over n, because PQ over n is the variance. Okay. So again, this is all about center, shape, and spread. We are studying sample proportions now. We've learned under certain conditions, sample proportions have bell-shaped distributions. Okay, so we're going to use the normal distribution to study sample proportions when NP and NQ are both bigger than or equal to 10. Okay. So that's the shape. It's bell-shaped. Sample proportions have a bell-shaped distribution. The center of the distribution is the population proportion, and the standard error describes the spread. It's this, sorry, the standard deviation, it describes the spread, which is the square root of PQ over n. Now I've used the word, I should be saying standard deviation, but sometimes we call standard deviation, also known as AKA p hat. P hat is also called the standard error. Not just standard deviation, but standard error. Okay, now you'll hear me using that word more and more. I don't see it here. Standard deviation of sample proportions. Now I'm going to call it the standard error of sample proportions, because a sample proportion is an estimate of a population proportion. When a standard deviation, sorry, when a sample proportion deviates, that deviation is an error in the estimate. So for example, look at this p hat value here of 0.5. Is it equal to the population proportion? No. If it is used to estimate the population proportion, any deviation in that estimate is an error. Okay. All of the sample proportions deviate from the population proportion. They all contain error. The standard deviation is therefore just a standard error. It's an average error. Okay, so when we work with statistics like a sample proportion and later a sample mean, standard deviation of those will always be called standard error. It's the same thing, and you can compute them with the same formulas we've computed standard deviations with before, but it just gets a new name. It's called standard error. Deviations become errors. Okay, and you can see here I'm deriving the mean, in a slightly different argument here and the standard error here. Okay, so that none of that's really new. Okay, but I think they're going to have us compute these somewhere. Ooh. I don't see myself actually doing this. Okay, so let me go ahead and do the computation here. The mean is P, which turns out to be 0.45. For the standard error, let's do this real quick. It's the square root of PQ over N. Just as a reminder, P was the proportion 0.45. Q was the proportion 0.55. If 45% approved, 55% did not approve. And then it was over N. The sample size was just 10 here. Okay, so we need to run that computation. Probably easier to do it in Desmos. Okay, so if you guys don't mind, do the computation and let me know what you get. Don't forget the square root. And I think 3 places after the decimal is just fine. Okay, any question? Anybody have an answer? And if you gave me 4 places, that would be fine. Let me see, let me double check and see what we did with the standard deviation below. Yeah. Anybody get the standard deviation or standard error now? I feel alone. Okay, I got 0.1573. I hope that's what you got. Okay, so 0.1573. I think you should notice the original standard deviation was 1.573. So look at the original standard deviation up here, 1.573. And just notice all we did was it's the new standard deviation is this number with the decimal place moved over 1. And that's because all the numbers in the distribution, these values, were divided by the sample size, which was 10. So if you divide every number in the distribution by 10, the standard deviation gets divided by 10. So it was 1.57. Now it's 0.157 here. Oops, hang on. Right here. So it's 1/10 as big as it was. That totally makes sense. Okay, the only thing that's left is just to kind of summarize everything that we've learned. And then I'm going to show you how to do a margin of error for a sample proportion. And it's all very straightforward. So we got the mean and the standard deviation of sample proportions here. And then the central limit theorem just tells us that the distribution is bell-shaped. Okay, so the distribution of sample proportions comma from samples, let's say p hat, from samples of size n, and then I'll have to add another comma, drawn from a population with proportion p, has the following properties. Okay, first, it is normal as long as NP and NQ are at least 10. And I should say, guys, we always say approximately normal here, so I'm going to fix this. So it is approximately normal. If NP is at least 10 and NQ is at least 10. Okay, any questions? So we have that from some time ago. Secondly, it has mean mu with a subscript of p hat. This is the mean of p hat values, so that's why we use a little p hat subscript on that. And the mean is just p. Thirdly, it has standard deviation or standard error. I'll say standard error, but in the word in parentheses, I'll say deviation. Sigma with a p hat equals the square root of PQ over N. Okay. And then finally, it is called the sampling distribution of sample proportions. It's just a probability distribution, but because the numbers all come from samples, these are sample proportions. So since all the values come from samples, they call it a sampling distribution. So it's a sampling distribution of sample proportions. Okay. Okay, any questions yet? Looks like all we're going to squeeze in here is just this lesson. So we won't, I don't think I'm going to go to 6.3 today, just FYI. Because I just don't see us fitting it in. Unless maybe I'm crazy, I don't know. We'll see. It's really quick. All the heavy lift, there's been a lot of heavy lifting to get through all this. So the next lesson's actually pretty easy in comparison. So I don't know, maybe we'll figure it out. Maybe we won't. I don't know. Let's see. Okay, so I want to go ahead and talk about this margin of error for a sample proportion. Now, this is going to be a distribution of sample proportions. So right on this first bell curve, I'm putting a p hat there. Okay, and the mean of sample proportions is p. Okay. And what I want to do is determine a margin of error. So just do a real big kind of a curly brace here. You're going to be putting a p hat in here. So wait a sec, that's too much. Hang on. Okay, so first of all, put a little p hat in here. There are many sample proportions. We're just doing one inside there. And then this whole thing right here is going to be the margin of error. Like that. Okay, and then same thing on this side. I'm going to do the margin for error here. Okay. And we just need to know how many standard deviations to use for a margin for error. Okay, so let me just go ahead and walk you through this. Oh, I should put another big E on this side. So we got a margin of error on both sides there. Okay, so let's go ahead and say the area in here is called the level of confidence. 0.95 is the area. So the level of confidence would be 95%. Okay, normally we use 95% confidence when we do this stuff. Okay, that's the area. I would just say 95% of all sample proportions will be within the margin of error of P. Just look at the picture. Okay, so look at that proportion there. And let me do a different color. Okay, so that little sample proportion is one of 95%. So 95% of sample proportions are within the margin of error of the population proportion. Okay, so the P, remember, in the middle here is the population proportion. Okay, 95% of them, that's actually the empirical rule. It's two standard errors. 95% of values are within two standard errors of the mean. And here the mean is the population proportion. Okay, two standard errors. So if the area in the middle is 0.95, okay, this z-score should be 2. Okay, but technically it's not exactly 2. Okay, so I have to tell you exactly what that z-score is. So I'm going to backpedal a little bit and show you something in Desmos. So let me do a new share. I'm going to go over to Desmos. Take me a second to get there. Desmos. Okay, logging in. I'm logged in. So I actually created a fun little Desmos document, right? Where is it? This guy here. Okay, so technically, you know, I can set this thing called the level of confidence to any value that's, you know, between 0 and 1. So if I want to do 99% confidence here, this spreadsheet tells me that I have to go out 2.56 standard errors from the mean. I have to go out to here, 2.576 standard errors left and right to capture 99% of the population. So that would capture 99% of sample proportions. Actually, I want 95% of them. That's my level of confidence here. So if I change this to a 95%, we've always said 2 standard deviations will capture 95% if it's bell-shaped, but technically it's 1.96 standard errors here. So I'm getting this from Desmos. 1.96 standard errors will capture exactly 95% of the sample proportions in the long run. So let me go back up to my iPad. Okay, so I'm going to change that 2 that I wrote here to 1.96. Okay. Here, the margin of error would be Z standard errors. Okay, Z is always the number of standard errors away from the mean. And we're saying our margin of error needs to go out this many standard errors. So it's called Z alpha over 2. You can kind of see the geometry here. Alpha is a Greek letter. Oops. It's the first letter in the Greek alphabet. Mathematicians love Greek letters. Don't ask me why. Second letter in the Greek alphabet is beta, and alpha beta is where we get alphabet from. So again, alpha is just an A in the Greek alphabet. Okay, so alpha here is 1 minus the level of confidence. So we're doing 0.95 for the level of confidence. Okay, so alpha would be, in this case, 1 minus 0.95. So this is 0.05. And that's the area of those two tails that I've shaded combined. Okay, so alpha over 2 here would be 0.05 over 2, which is 0.025. Okay, and knowing this area here will help you determine this z-score. It turns out to be 1.96. Okay, and there are easy ways. I just showed you a really easy Desmos tool for that, and I'll put a link for that in Canvas when we need it. I won't need it till next week. Okay, but once you determine how many standard errors you need in your margin for error, remember z-scores are just the number of standard deviations or standard errors. This number of standard errors will give the margin for error. And if you're using 95% confidence, then 95% of these sample proportions will be within the margin of error of the population proportion. So my margin of error would just needs to be this z-score. It's called z alpha over 2 because it separates out this upper tail whose area is alpha over 2. Okay, so z alpha over 2, the number of standard errors, but we have a formula for the standard error. This would be z alpha over 2 times the square root of PQ over N. This is our margin of error, and I'd rather say margin for error. In a sample proportion. Okay, so it's just, and this number is always around 2. Okay, technically 1.96. Okay, and just think about the empirical rule. This is the empirical rule, but it's kind of an ugly version of it. We've always said that if it's a bell-shaped distribution, and this will be bell-shaped if the conditions are met, right? What are the conditions? Where to go? It's going to be normal if NP and NQ are at least 10. So if it's bell-shaped, then 95% of the values are within 2 standard errors. So that's why we're doing something that's close to 2 standard errors every time. Okay, again, standard deviations, they're standard errors. So about 2 standard errors, that captures 95% of the values so for 95% of the time, if we use this for our margin for error, the distance between the estimate and the thing that's being estimated will be less than the margin for error. Okay, so sometimes I call it margin for error, but sometimes I call it a maximum error. That's it for today, everybody. I do have an office hour in about 10 minutes. So I can take questions for a few minutes, then I'm going to do a little bit of a break. A lot of you guys got comments this morning from me on, some of us are going back and forth on proposals and sort of a little wrestling match trying to get everybody to sort of agree, me and you guys, to how you're gathering your data. So I think 4 people submitted by Wednesday, and I've read those, and most of those are good. One of them still had a comment, but take a moment. If you just turned in your proposal again this week, take a moment and look at my comment. One person I had additional questions for, but otherwise you're good to go. And you guys can, once that's settled, you can go ahead and start collecting your data. The instructions are in that assignment in Canvas. I can't think of anything else I didn't say. Remember, you're going to be doing that review. It's due Friday morning at 8:30. I'll be posting the solutions on Wednesday so you can make sure you understand any mistakes you made. Are there any questions? All right, my students, it's always fun working with you. I wish I could see your faces, but that's life. And so I'll see you. I've got an office hour again at 11:45, so that's in 10 minutes. So, oh, and I forgot to take roll. Forgive me. Oh God, you're going to be so angry. I'm going to take roll.
I thought you did take roll after break. You had to roll.
I did.
Yeah, and then it was like only a few students that were missing.
It's really scary when you just forget stuff like this. Thank you so much for your help.
Yeah.
Any of you guys that were here when I missed when I took roll, just put your name in the chat and I'll fix it. Just tell me that you're here. If you didn't hear me call your name before. Bye, everybody.
Bye, thank you.
I got you, David. Thank you.
Bye, thank you.
Thank you. Thank you. Thank you. Okay, so this is section 6.3. I can just we just jump right in here. We're going to use the results from the last lesson, primarily the margin for error formula that we have here to compute what we call a confidence interval, which is just basically your estimate plus or minus the margin for error. So it kind of sounds weird, but it's nothing more complicated than that. Okay, so just to make sure, let's read through this. It says, in this lesson, we construct confidence intervals for population proportions. This uses p-hat, which is the sample proportion, the estimate of the population proportion, and a margin for error. Maybe just a couple of notes here. P-hat is x over n. This is sample proportion. Okay, P is population proportion. Okay. So let's go ahead and just walk through the steps here. First thing you need is you're going to need the p-hat. So we'll go ahead and say p-hat, you need, this is x over n. You're going to need n. You're going to need a level of confidence. And you're going to need alpha, which is 1 minus the level of confidence. Okay, any questions there? And it says, and check. The check part is that n times p-hat, which I have talked about, turns out to be the number of successes in the sample. That's an estimate of n times p, which has to be at least 10 for the left tail of the binomial distribution to taper off like a bell curve. Same thing as in q-hat, which, as we've seen, is the estimate of the number of failures. it's the estimate of n times q, which is the average number of failures. Here, we're just going to say this is the number of failures. Again, that's the right tail length on the binomial distribution. We want this to be bell-shaped. So the right tail needs to be at least 10 in length as well. And that gives it enough room to taper off on both sides. Okay, so the lookup part, remember we're saying your margin of error is just basically around 2 standard errors, but the actual number of standard errors depends on how often you want to be right, how frequently, I should say, you want to be right. So what you're doing is trying to get this z-score, which is the number of standard errors. So let me just kind of remind you the picture here has these 2 cutoff values on a z distribution. The level of confidence is inside here. I'm just going to write conf in there. And then the tails are alpha over 2. Okay, and then you get this z-score z alpha over 2. That's the number of standard errors and the margin for error. Okay, now how do you get this? Well, I've got the area of the right tail. Now, if you're going to use table A1, then again, the right tail area is alpha over 2 here, but I need to know the area to the left of a z-score when I use table A1. So really, you're looking for something that's close, just as close as you can to 1 minus alpha over 2. Okay, and that will give this z alpha over 2, which we call a critical value. Okay. And then the hundredths place is up here. Oops. Like that. So that's one way to do it. Easy enough. Any questions? You may want to start using table A2 now. I don't think I start using table A2 until a couple sections on in the book, but I'm going to go ahead and start showing you this now because it's actually a lot easier to use. Okay, so for table A2, all you have to do is go down to the bottom row. There's a column called DF that stands for degrees of freedom. That's for a distribution we call the T distribution. The T distribution approaches the Z distribution. So in the very bottom row, it just says large. When degrees of freedom are large, you're looking at the Z distribution approximately. So T distribution eventually becomes the Z distribution, which is in the bottom row. Okay. What you want to do is look up your alpha under 2 tails. I'll show this in a minute. Okay. And in the very bottom row of the table, this is super easy. In the very bottom of the row of the table, you'll just see your Z alpha over 2. So you just need an example of that in a minute. So that's 2 different ways to get that. You can get it with table 1 or table A1 or table A2. They will have the same value. Use whatever you feel most comfortable with. Table A2 is a little more precise. Okay, any questions? Okay, now the margin for error is just Z alpha over 2 standard errors. So the margin of error is going to be Z alpha over 2, which is always around 2 standard errors. Okay, and so I can use the word standard error here, or just put in, I think I'll do that, standard errors. Okay, which to be explicit is Z alpha over 2. And then the formula we figured out for the standard error is the square root of P times Q over n. Now I'm going to change this because just remember, we're estimating the population proportion. This sentence right here, the margin for error uses p hat, the estimate of p. You're estimating p, which is another way of saying that p is not known. And that's another way of saying you can't compute this margin for error because it requires p and q. And so, of course, we'll use our estimate of p, which we call p hat. And the estimate of q, I guess, we'll call q hat, which is new. So just as a kind of a note over here, q hat is 1 minus p hat, just like q is 1 minus p. All from the binomial experiment. That's the underlying theory and everything I'm saying. Okay, so the endpoints of the confidence interval, you're just taking your estimate plus or minus the margin for error. So that sounds kind of scary, but it's not. Okay, so the endpoints are p hat plus or minus your margin for error. Okay, now what this means is that the population proportion, which is unknown, p, should be, I'm not saying will, I'm saying should be between the estimate plus or minus, so on the left I'll say minus margin for error, and the estimate plus the margin for error on the right, okay? So the level of confidence is the proportion of intervals that are actually true. So we'll make that note. The level of confidence is the proportion of such intervals that are true. Now, if you don't like that, I could say the proportion of such intervals that contain P as advertised. So sometimes these are wrong. All right, so we're almost there. I'll take questions in just one sec. To interpret this, I'm going to just help you out and give you a sentence that you can almost fill the blanks on. You can say, we are, oops. Okay, you're going to say blank percent confidence. And there you're going to fill in the level of confidence. Okay. So here you're going to put in the level of confidence, but convert it to a percent, I guess. Okay, any questions there? Blank percent confident that between blank percent and blank percent, between blank and blank percent of some categorical variable are meeting some criteria. Okay, so I'll put in that on this first part, the first blank is going to be p hat minus e. So here, this will be, you'll fill in whatever p hat minus e is on the first one, and you'll fill in p hat plus e on the second one. Like that. And then on the next one, you just whatever your categorical variable is. Okay. Are events that we call successes, whatever the successes are in the binomial experiment. Okay, so that last sentence probably needs to be demonstrated. And because it's like, well, what is all that? It's a fill in the blank. It's a Mad Lib. Just randomly put stuff in there. See how many points you get. I'm kidding. I have to say I'm kidding. Okay, so do you guys want to ask any questions about the theory that I've just presented? Obviously, you need an example. I'm not seeing any questions, so I'll go on. You may have example or questions once we go through an example. And I would just say, please do interrupt me at any point if you are confused by something. Okay, so there's a simple, look how much space I give. So I've got a pretty step-by-step process here. And I'm saying in 5 steps that you can you can fit it in this little 1.5 inches of space. I don't know if I believe it, but I'm gonna try. Okay, you guys all right? All right then. So it says we've got 900 voters randomly selected, and 414 say that they're going to support the Democrat who's running for president. Great. So you're doing polls now. And with polls, we're going to get percentages, and the percentages come with margins for error. So obviously, that's what this does. So let's see if we can pull this off. Step 1 says we need the p-hat. We probably get all these other numbers and then check number of successes, number of failures. All right, so I'll just try and squeeze this in here. So our first step is we need p-hat, which is x over n. That's the 414 over 900. Let's do 3 places after the decimal. I'm going to get my calculator out and I expect you guys to do the computations here. So you can just shout it out when you get it.
.46.
Yeah, 0.46 is fine. Thank you. So that's p-hat. Our n is obviously 900. I won't write that down. I'll just maybe just flag it here. This is n. Okay. We need the successes and the confidence level is 0.95, which means our alpha is 0.05. So keep that in mind. Then the check. So you count the number of successes, and the successes are n times p-hat, but don't lose sight. You already know this. It was 414, and that's more than 10. Much more. So you're like, okay, this is fine. This will absolutely work. Questions? The fails are the non-successes. That should be easy also. So the fails are going to be 900 minus 414. So what's that? Anybody?
.486.
Correct. Again, that's also got to be at least 10. Now, so we're good to go. Any questions about that first step? I think the second step was getting the Z alpha over 2. So let's do that. I'm going to try and do both tables and squeeze all that in here. So if I do table, this is step 2. If I do table A1, then you're searching in the table for something that's approximately 1 minus alpha over 2. Oh, wait, is this one at the bottom? I'm wondering if this is one of the ones that's at the bottom of the table. So let me look at this real quick. So at the bottom of this table, not really. Okay, so never mind. That's fine. So we're looking for something that's approximately 1 minus alpha over 2. So now you just got to remind yourself the alpha was 0.05. So what's 1 minus 0.05 divided by 2? Anybody? Don't forget alpha is 0.05. So has anybody got that computation?
Is that 0.975?
Good, 975. I'm going to add the 4th digit because table A1 has 4 digits there. So the 4th digit that isn't displayed is always a 0. If it terminates, then it's just zeros after that. Okay, so we're looking for a 0.9750. That means I got to pop back over to that table and search it in the body of the table for a 9750. This is one of the rare cases where you'll exactly see that number. So let me highlight it right here. And then obviously we're going here and up there. So he says that says 1.96 there. Okay, any questions? That's the, 95% of sample proportions are within 2 standard deviations of the mean. It's not exactly 2, it's 1.96. That's the real number. Okay, when we say that 95% thing. Okay, so 1.96, let me find the notes again. Here they are. So this goes out to 1.9 and 0.06. Okay, so this tells us that our Z alpha over 2 is 1.96. Okay. Questions there? Just to show you table A2, so much easier, I'll just say or table A2, your alpha is 0.05. Make sure you look under 2 tails because the alpha gets split between the tails. That's the alpha over 2 part. And it's kind of common to forget this. People sometimes, oh, dang, it's 2 tail, not 1 tail. This table does both. You go down to the bottom row where the Z-scores are. This is where the degrees of freedom gets large, whatever that is. It's been a long time since I talked to you guys about degrees of freedom, but I will be talking to you about it again soon. Anyway, you go to the very bottom row, make sure you're looking at 0.05 2-tail for alpha, and you'll see a 1.960 there. I'm just going to show you the table real quick. And I'm going to, ooh. Yeah, okay, so this is actually in these notes. So I have to slide down a ways. So if you go, are these still not numbered? What a tragedy. The very last page of these notes is table A2. Okay, And so all you're doing is finding under two tails, find your 0.05 alpha there. Okay, and then you just take this to the bottom row. The very bottom row, and you should see a 1 point, very small here, but in the bottom row it says 1.96. Okay, and all of the alpha values that you could possibly need are here, going from a 0.01 alpha all the way up to a 0.2 alpha, which I don't see us ever doing because nobody wants to be 80% sure. Okay, 0.02 alpha is when you're doing 80% confidence. Okay, any questions?
How do we know like to go all the way down, like right there?
Yeah, this distribution is called the student's T for T-scores and normal distributions. Okay, and then what the heck is that? The normal distributions is for Z-scores. So if you just look, those are where the Z-scores are. And how do you know? Because I told you. Okay, if you're going to use this table, that's how you use it.
So it's just that last row, that's a Z-score?
It says so, yes.
Oh, okay.
So the rest of these are T-scores, which are more complicated because they depend on degrees of freedom. And we'll talk about that later, not much later, it's coming right up. Okay, but if you're going to be using this table, you just need to remember that last row has all the Z-scores for every confidence interval. You'll never, there's no confidence interval where the Z-score is not in that bottom row. Okay, and they'll be varying the level of confidence, which determines which Z-score you're using. There, as we've said, it's always around 2 standard deviations, but it's really between 1 and 3 standard deviations, just depending on how confident you want to be in your outcome. Is that okay?
Thank you.
You bet. Cleaning up just a bit. All right, so back to where we were, see if I can find that. Okay, so we've got our Z-score now. The third step, the rest of this goes pretty easy. So step 3, we can do our margin for error. So the formula is E equals Z alpha over 2 square root of P hat Q hat over N. All right, so the Z alpha over 2 we determined was 1.96. P hat is up there. It's what? I forget. Oh, no, it's here. It's 0.46. So we can put in 0.46 times Q hat. Well, Q hat is 1 minus P hat. So maybe I'll do that over here. I don't know where. Q hat is 1 minus P hat. That's 1 minus 0.46, which is 0.54. And then I'll just nudge this down just a bit. There we go. So we'll put in a 0.54 for Q hat. Like that. And then N was 900. And you'll see that routinely, when your sample sizes are around 1,000, this is pretty close to 1,000, that your margin for error is around 3 percentage points in general. So here is where I'm not sure how you're computing this. I'll use my standard, which is Desmos real quick. So let me see if we've got that open still. Yes, I do. Okay, so I'm going to share back over to Desmos right there. And so here, you want to do the 1.96, you can say times, which is an asterisk. And then the square roots are on the little toolbar that I'm waving at right now. So if you pull that up, press the square root, okay? then I would just do this fraction bar first. So type the fraction bar, which is just a slash. And here you can type 0.46 times 0.54 in the numerator, and then use a down arrow to get that sample size in of 900. And so there's your margin for error. You can see it's about 3 percentage points, 0.03. Okay, we're gonna keep 3 places, I think, here. So let's do 0.033. So I'll just remind you, whenever we work with proportions, I've asked you to keep 3 significant figures on those. This is the margin of error for a proportion, so it gets the same rule. Okay, so I'm just going to say 3 sig figs here, which means, dang it, I need one more digit. 04326 is what that should have been. Okay, so just as a reminder, we don't count leading zeros. Okay, any questions there? So now you got a margin for error. Like I said, 3 percentage points is typical for something close to 1,000. This is 900, which is a little below 1,000. So we see the error a little bit above 3%. Smaller margins, sorry, smaller sample sizes yield larger margins for error. Okay, let's do question 4, which is the endpoints for the interval. So this is where you come in and you go, all right, well, the interval is p hat plus or minus the error.
Professor,
Question?
are we supposed to still be looking at Desmos?
Oh, my bad. No. There you go. So 3 sig figs for that computation, 0.0326. And then we do our confidence interval, p hat plus or minus the margin of error. So first you subtract, p hat was 0.46 minus the margin for error, 0.0326. We'll round this again when it's done. And then you add the same 2 numbers. So I'll round that to 3 sig figs again in a minute. And if anybody could just tell me what you get before you round it.
Is it 0.4274?
Correct, 0.4274. Anybody do the other one?
0.4926.
Right, 0.4926. We round these now to 3 sig figs like the rule says. So we do 0.427, so it's 42.7%. And then this other one would be 49.3%, 0.493. Now the confidence interval, it actually should be stated as an inequality. So what you're saying is we think the population proportion is between 0.427 and 0.493. Okay. Any questions there? So the only thing that's left is phrasing this funny interpretation. Okay, so the interpretation is we are blank percent confident, right? So let's squeeze that in here. That between blank and blank percent. So we are 95% confident that between 42.7%, and 49.3% of, what's the next? The categorical variable. These are just the voters. Okay, they fall into categories, right? So we could say the votes. Oops. Are, how do I say it? Successes. So that is to say, voting for the Democrat. I guess I have to use a capital D on that, right? Okay. So that's just how you fit all the pieces together in that puzzle. Any questions there? That's pretty much statistics. 2 standard errors. That's what you got to account for. 2 standard errors in your margin for error. Yeah, okay, 1.96 standard errors. Now, okay, it depends on the level of confidence, fine. 2 standard errors. Any questions? Now, if you ran these intervals thousands of times, you'd see about 95% of them actually are true. So I'm going to show you a real quick demonstration of this. So just a real quick, they use a little bit different notation. Let me share this with you real quick. Okay, and this is just a simulation. It's random. And so you can't control randomness. You know, we say 95%, but we mean in the long run, 95% of the confidence intervals will contain the population proportion. So what we do here is I just want to remind you, I'm going to zoom in on some of this. First of all, the Greek letter for P is pi. That's a pi right there. That's in this simulation, they use pi for the population proportion. And I think we said 40. Oh, I don't know the population proportion. What am I doing? This is hard because I don't know the population proportion. I'm going to use 46. So we're going to go, we had 46 from the sample, so I'm going to use 46 for this. Okay, so 46% is my estimate of the population proportions. I'm going to do 1,000, samples of size. What was our sample size? 900. Okay, and then if I just do one interval, it does this little teeny confidence interval. And you can see if the population proportion is 46%, which I don't know that it is, you can see that the 46% is contained between the low, I can actually click on this. The lower limit of the interval is 0.441. The upper limit of the interval is 0.506. And this interval here is containing the population proportion. Okay. I want to do more than one interval, so I can actually tell it, I think I can tell it to do 100 here. And so what it does is it'll plot all 100 confidence intervals. Okay, and you can see the green ones are the ones that contain the population proportion, which I'm pretending is 46% right now. The green ones cross this black line, which is at 46%. You see this red one here, it goes from 38.9% to 45.3%, which does not make it up to 46%. So this, and I can actually click on that interval and it will show that these estimates here give bad confidence intervals. The one I just clicked on is this low estimate, which gives a bad confidence interval. Okay, the ones that are in red, I have to click away from this. So the ones that are in red are the bad confidence intervals. And you can see there were 3 out of 100. So this time we actually got 97% of these to contain the population proportion. So in the long run, we mean that it's 95%. In the short run, you can get all kinds of things, but it'll tend to be around 95% of the intervals. You see down at the bottom here, there's the other two intervals that came from really high estimates. Those extreme estimates, this one and this one, are the two estimates that are on the tails of the bell-shaped distribution. The ones that are on the tails of the distribution are outside of that 2 standard error range. And those are the ones that are going to give margins for error. Sorry, those are the ones that are going to give confidence intervals that miss the population proportion. Okay, I can do thousands of confidence intervals. So now I'm going to do 1,000 of them and ask it to do its trick. This time I got 95 point, well, in the long run, they're saying it's 95.1% of all the intervals it did. That counts the previous 100 intervals. So I've actually done, the very first one was the 1, then I did 100, and then I did another 1,000. So with a running total, they're saying 95.1% of my intervals are containing the population proportion. This is kind of a furry little graphic, but you know, you can see this, a lot of the times I'm wrong, but again, 95% of the time I'm right. Okay, I'll just pause for one moment and see if you guys have any questions about that. It just depends on your data. If you end up with a sample that yields a really bad statistic, and they do that, so good samples yield bad statistics sometimes, even when you do everything right. Data can, it's a sample, right? And if you're using a sample to represent a population, most of the time you're going to be okay. 95% of the time you're going to be okay if you use 95% confidence. But the other 5% of the time you're not. And if that's no good, you're going to have to increase your confidence level. I think I should show you what happens when you increase the confidence level. I'm going to change this to 99%. And then ask you guys to look very carefully at how wide the intervals are. So if I change this to 99 and recalculate, what happened? Anybody? Anybody see what happened with the intervals?
There was a bit less of the red lines.
Well, there's fewer red lines. That's true. But I don't know if you noticed, but all of the intervals got thicker. They got wider. And so it's sort of like shooting an arrow at a target. If you're gonna say, hey, I want to make more of these shots when you're shooting at I want to hit the target more often. The easiest way to do that is make the target bigger. That'll raise your confidence level. Okay, and that's all that's happening here. When I said I wanted to be right 99% of the time, all of the intervals got wider, which means it was allowing for more margin for error. Okay, if you allow more margin for error, then you're going to be right more often. That's sort of logical. And notice this time I was kind of lucky. I did 1,000 intervals and at exactly 99% of them contained pi, which is what this thing calls the population proportion, which is that which we're pretending is the 46%. Generally, you don't know the population proportion, but if you're using 99% confidence, your interval is going to contain the population proportion 99% of the time. But the penalty is that you're going to have to report a larger margin for error. You know, you're going to hit larger targets more often. Okay, but people aren't as impressed when you have a larger target. Okay, so it's sort of a trade-off. 95% is sort of the compromise confidence level. Okay, it doesn't return a really big margin for error, but you're still right 95% of the time, which ain't bad. Okay, any questions about that one? So it's important. Oh yeah, go ahead.
I was just wondering, is that going to be a useful source for homework in the future? Like, are we going to need to have that?
What I just showed you?
Yes.
No, it's nothing more than wanting you guys to understand what we mean when we say we're 95% confident. It
Right.
just, it just means 95% of the time you'll be lucky. And you'll be saying something that's true. But it's so important for you to understand that in statistics, sometimes you're wrong, and that depends on the probabilities you set up, right? If I want to be 95% confident, that's fine. You're going to be right 95% of the time. That's up to you. It's your choice. Okay, but you're going to be wrong 5% of the time. I just want you to understand the trade-offs here. Okay,
Gotcha. Okay, thank you.
no problem. Anybody else? Okay, so let me go back to the iPad. How are we doing for time? We've got 10 more minutes before I stop. So let's try and squeeze in the other example here. I think we can do that. Oops. Okay, so we're going back. It's just this next page in the notes. So it's almost identical. I'm not going to go into this part where we talk about managing the error, but I want to go ahead and look at this example here. So it says, in a Gallup survey of 1,100 registered Republicans, 175 state that climate change will affect their lives. This was a few years ago. It seems like the Republican Party has become a little more extreme about things in general. People might argue that the Democrats have become more extreme as well. I'm not going to get into the politics, but I am saying that I think that these numbers may be different right now. Okay, this was based on a poll that was several years ago. Okay, so they want a 98% confidence interval this time. Okay, for the proportion of Republicans who believe climate change will affect their lives. Okay, so I'm going to walk through the steps again. Step one, we had to get that p hat value. So that's x over n, the formula. The x is the number of successes, 175 out of 1,100. That seems like a pretty small proportion to me, and it's sort of alarming. So we've got 175 divided by 1,100. And again, 3 significant digits. Anybody? Okay, so
0.159.
yeah, 0.159. Thank you so much. And then we have to count successes. Clearly it's 175. And again, clearly greater than or equal to 10. The fails are 1,100 minus 175. Anybody? This one's 925, just FYI, which of course is greater than or equal to 10. We need our confidence level. So the confidence level was 0.98. A little weird. The alpha will be 1 minus that. So this is going to be 0.02. Okay, any questions there? I think step 2 was getting this z-score. So again, I'll look at both tables. So if you look at table A1, you're looking for something approximately equal to 1 minus alpha over 2. So you can probably do this in your head if you think about the percentages. Alpha over 2 is 0.01, which is 1%. And you're doing 100% minus 1%, which is 99%. So this is going to be 0.99. Okay. And you're not going to find a 0.99 in the table. I'm going to go ahead and just remind you, this table is on the second to last page here. So if you look for a 0.99, there's a 9901, which is really close. Oh, I lost it. It got away. Geez. Oh, here it is. 9901 goes with a 2.3 and then up to something up here, which is going to be 0.03. Okay, so any questions about the 2.33? That's to the nearest 100th.
I'm confused. How'd you get the 0.99?
Okay, so it's always one. Oh, why did I go there? It's always 1 minus alpha over 2. So if you do that computation here, you'll get 0.99. Alpha was 0.01. Sorry, alpha was 0.02. So I'll do it
Okay.
over here. 1 minus alpha over 2 is 1 minus 0.02 over 2. So that's 100% minus 1% basically, which is 99%. And that's why we were scanning for a 0.99 in the table. What you see is a 9901 there. And that corresponded to a 2.33. Like that. Okay, and so that's our Z alpha over 2. I'm going to go ahead and do table A2 also. So for table A2, for degrees of freedom, bottom row where it just says large. Okay, here our alpha is 0.02 and it's two-tailed always. Does anybody want to flip to the last page and look that up? It doesn't, this table A2 is more precise. So it doesn't say exactly 2.33 there. It's a better number than that. It's close, but it's just more precise. That's fine. I'll show it to you. So you just go to the 0.02 alpha, which is under two tails right here. So it's just a second column there. And I'll highlight all the way down to the bottom row. And the better value is 2.326, which rounds to 2.33. So they're compatible tables, but this is just a little more precise. I mean, you do it either way. On the next exam, I'll compute it both ways and take either one as a correct answer. Okay. Any questions? So it's 2.326. So I have to find my page again. Okay, so that's our Z alpha over 2. Okay, so then I'm just going to use that one this time since it's a little more precise. Either one's fine. The next is the margin for error. So E is Z alpha over 2 square root P hat Q hat over N. Just maybe remind ourselves Q hat is 1 minus P hat, which is going to be 1 minus 0.159. Could somebody run that real quick?
.0256.
I don't think so.
0.841.
Yeah, 0.841. Run that again. I think maybe you typed something wrong.
Yeah, no, my bad. I'm
Yes, okay.
ahead.
It's all good. So the Z alpha over 2 is 2.326. And then square root of P hat, which is 0.159 times Q hat 0.841 over N. This time it was 1100. Okay, I think the margin of error gets a little bigger here because we raised the level of confidence. So once again, I think this will be over 3 percentage points, but not much because we have a bigger sample size. And you can see the sample size, if you increase that, your margin for error goes down. So those are counteracting each other. We'll see how it comes out. And if you just go back to Desmos, you can just put the new values in. So change the 1.96 from the last one to 2.326. And then you can put in the 0.159 and the 0.841 and change the sample size to 1100. Oh yeah, so now the margin for error went down. So this is quite a bit lower because of the larger sample size. Anybody? And I think you can do 4 digits this time. So 0.0 something, something, something.
Two fives, 4, 5.
So you say 250,256 is what I've got. Does that sound right? Okay, good. Great. So let's just put that in 0256. Make sure y'all can do that computation. It's getting a little ugly. And let's just wrap this thing up. So step 4, our p hat minus e is going to be 0.159 minus 0.0256. So 1334 is what I got. So which we'd round to 0.133. And then when you add them, I got 0.1846. So that's p hat plus e. Same computation, but adding. So it's actually a different computation, 256. So that's 0.1846, which will round to 0.185. Okay, so this is once again hoping that the population proportion is between two numbers, 0.133 and 0.185. We have a small margin for error due to, again, a larger sample size. And that larger sample size kind of set off the higher level of confidence. In the end, we have some pretty good results here with basically a 2.5% margin for error, this number up here. Okay, so we'll just write our sentence. We are 98. I think it was saying 99, but it's 98% confident that between, I don't even know what this is, 13.3% and 18.5% of what's the variable here? Republicans believe climate change, which will affect their lives. Okay, so if you want to manage your margin for error, you just want to take this formula for the error. Like that. And we can just solve it for the sample size. Simple as that. So let's just take a second to do that. I think I'll square both sides. So you'll get E squared is this Z score squared, and the squaring makes the square root go away. So I'm just going to put a P hat and a Q hat. And I think I'll divide the whole thing by N because it's just easier to look at it that way. It's the same thing. And then we just multiply both sides by N. And that'll cancel the N on the right. And if we want, we can divide both sides by E squared to get rid of that on the left. Like that. So what this becomes is that the sample, and I could cancel the E squared on the left here. So the sample size should be at least this many individuals. You would do Z alpha over 2 squared times P hat times Q hat. I think I left my hat off over there. Let me fix that. So P hat, Q hat, and then you have to divide by your margin of error squared. Okay, there. So this is going to be our sample size formula. And it allows you to choose the margin of error that you want. If you don't have a sample yet, you have a little bit of a quandary here. The formula requires a P hat and a Q hat, which are sample proportions. And you're still trying to decide your sample size. So you may not have a sample proportion yet. You can do what they call a pilot study and gather preliminary information and get estimates for this. And this is common in research to do these kinds of studies to get our kind of dip our toe in the water and see what some of these statistics might look like. If you don't know P hat, let's just say have a sample proportion, a P hat value. Note the following. Remember, Q hat is 1 minus P hat. So what I'm going to do is I'm going to put a little table here of P hat and Q hat values. So P hat here and Q hat here. And then here, I'm going to put P hat times Q hat, which is in the formula. And I want you to see that this actually can only get so big. So I think I'm going to write pretty small here and put in 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and maybe 0.9, just to show you what these values come out looking like. The Q hat, remember, is 1 minus P hat. So this would be 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1. So these all, in every case, they add up to 1. Okay. And when you multiply them, 1 times 9 is 9. So this is actually 9%, 0.09. 2 times 8 is 16, so 16%. 3 times 7, that's 21%. 4 times 6 is 24. And then 0.5 times 0.5 is 0.25. 6 times 4, 7 times 3, 8 times 2, and 9 times 1. 0.09. So you see what's the biggest this can get? Right there. If P and Q are both exactly a half, the biggest P hat times Q hat can be is 0.25. Okay, so the note we'll add here is P hat Q hat is never bigger than 0.25. Okay, so we will kind of use that to simplify the formula a little bit. There's it's sort of a penalty. You're sort of saying, well, what's the very biggest it could be? And then you're using that to determine how your sample size, how big your sample size should be. And the disadvantage of doing that is that sometimes P hat times Q hat is actually really small. So if it was closer to 0.09, I mean, 0.25 is almost 3 times bigger than that. So if you're using 0.25 and it's 3 times bigger, then your sample is going to come out 3 times bigger than it needs to be. So, and that means it's going to cost 3 times as much money to do all that data gathering. So this thing where all the books tell us, well, just put in a 0.25 if you don't know what to do for P hat and Q hat. That can be a bit of a waste. But let me go ahead and fill in what we've got down here. So you get to, so let's see how to put this. You can choose a value for E. I'll just say E, which is the margin for error. But you must sample at least this many. And again, at least make sure you understand that means no less than. And so that's going to affect our rounding rule. I'm going to say don't ever round that to a smaller number is what I'm going to say. No less than is what this says here. So you must sample at least, let's just put this formula in, N equals Z alpha over 2 squared, and we'll put the P hat, Q hat over the margin of error squared. And that's assuming you have a value for P hat from like a pilot study. So this assumes P hat is available. Okay. And then I'll say, or there's no pilot study. So here you would just do N is Z alpha over 2 squared. And instead of P hat times Q hat, the rule is no less than. So I'm just going to make this as big as it could possibly need to be by putting in a 0.25. Okay. And then we divide by our margin for error, which we're picking out of thin air. Okay, squared, divide by the margin of error squared there. Okay, so I would say just as a note, this would be if there's no P hat given or available. And generally, a pilot study just means you go out, you survey 100 people. You know you're going to be doing probably 1,000. So if you just quickly do 100, you could get a P hat from that, and then run the number on this formula, and that'll tell you how many more you have to do. Okay, so that's not a burdensome thing and might be worthwhile. But let's see, if you kind of look through this, we have a p hat in the last problem. So just kind of going back, we could view this one as a pilot study. 0.159 is our p hat value with a sample size of 1100. Then that gave a margin of error about 2.5 percentage points, 0.0256. Now, if that's too big, then obviously the answer to the question of how do you round or how do you make this smaller is to increase your sample size. But you don't want to just take a shot in the dark. Well, how big should the sample be? And just guess. We can tell you how big the sample needs to be. Okay. So if we come back, what's the confidence level? It's still 98% confidence here. So that means we're going to use the same z-score, which turned out to be 2.326 here. Okay, so if you just run the numbers, we can say n is z alpha over 2 squared and p hat q hat over margin of error squared. Now, they've given us a 2 percentage point margin of error. That just means for E, you're going to use 0.02. Okay, so you're picking your margin for error, but then you have to sort of let go of your sample size when you do that. Okay, and then with 98% confidence, that's what determines your z-score. So just a reminder, you can find that on table A1 or A2. In table A2, which is the one I recommend, just as a reminder, alpha, you've got this level of confidence, and alpha is 1 minus the level of confidence. Okay, so it's 0.02. And so on table A2, you just look up your alpha, 0.02, make sure it says two-tail there. And this gives a 2.326 Z alpha over 2. And so that's what I'm going to use down here. 2.326. We have to square that. And then again, get our p hat value. So going back up here, the p hat was 0.159. We also need the q hat. So over here we did q hat, it was 0.841. Okay, so 0.159 times 0.841 is what we need there. Like this. And then dividing by our margin of error. This is a chosen margin for error, but it's got to be squared. So 0.02 squared. And either compute this in Desmos or on your calculator. And I'll just wait and see if you guys can get this.
I got 1,808.641.
Good. Thank you so much. 1808.6. We're going to round this up. So 1809, 1,809. This is a little bit picky, but I just go ahead and mention this over here. You're going to always round this up. So it's not really rounding, meaning, but the point, write down whatever you need to here to remind yourself rounding up means you don't ever make it smaller. You want to make this a whole number because it's a number of individuals, but it should be bigger than whatever comes out here. So 1808.6, obviously we need it to be at least 1809 to get the margin of error we want. Again, it's not that big of a deal if you went down. Okay, but the rule is to go up to a larger number. Okay, you guys have any questions about that? Now, just to make sure we understand what we've done here, we started with a sample of 1,100, which is pretty big, okay? And usually with about 1,000 individuals, you get about a 3 percentage point margin of error. This is little more than 2.5 percentage points. So it kind of rounds to 3 percentage point. Okay, it's a little less because our sample size is more than 1,000. Okay, and other variables as well. But it usually comes out about a 3 percentage point margin of error. Now, we're trying to get it down from this 0.0256 to just 0.02, which is a teeny change in the margin for error. You got it? From 2.5 to just 2 percentage points in our margin for error, you have to increase your sample from 1,100 to over 1,800. Okay. That's really painful. That's the problem is as you start to push this margin of error down to 0, you're dividing by a number that's getting closer and closer to 0. And dividing by numbers close to 0 just makes the answer explode. It gets bigger and it goes just right through the roof. If you wanted a margin of error of 0.01, I'm just going to show you. Just note for a margin of error of 0.01, your n needs to be. I'm just going to go back in that last calculation we did and change the error to 0.01. Now it's 7,234.6. So I'll say 7,235. And maybe followed by the word ouch. So again, you have to think about people have to pay for this research. You have to pay employees to go out and gather the data. And we've gone from a 2.5% margin for error down to a 1% margin of error, which is great. It's super precise, but it's going to cost you. It's going to be over 7,000 people in your study. When we were closer to 1,000 in the beginning, we've gotten this margin of error to get small, but the cost has gone through the roof. So you see the trade-off here. It's really hard to get margins of error that are close to 0. And that's why people normally are happy with about a 3 percentage point margin for error, which comes from samples of a size 1,000, and going below a 3 percentage point margin for error is just almost too much to ask. Okay. So it depends, in huge studies, they'll do that. And sometimes people do huge studies, but that, again, those are expensive studies. Okay, any questions about all of this? That is it for that. Oh, sorry.
Yeah, I think it's also interesting what happens if you take 0.25 as if you don't do the pilot study and you take 0.25, like you like almost double your sample size.
Right, exactly. So that's a good point. So I don't know where to squeeze that in, but I want to put it in. That's terrific. So if no p hat is known, now I don't know which margin for error to use. I'll just say with E equal to 0.01 still, just to make it as brutal as possible. So is that what you did, Dan?
Yeah, it came out to 13,526.
Okay, so yeah. And people do studies really big like this, but not very often. It's just astronomical, really. So you think about think about all the work it would be to gather all that data. So any questions? Yeah, that was really interesting. Thank you. Okay, so that's it for that one. I'm ready to go on into, so here we've spent all our time studying distributions of sample proportions. What we haven't studied is distributions for sample means. So we have to look at that. We need to find out the center, shape, and spread of that distribution, so that we can do the same thing for sample means that we did for sample proportions, which was primarily to get a margin for error. And then later on, we'll be doing hypothesis tests on sample means, just like we'll be doing on sample proportions. Okay, but it all depends on knowing the distribution that you get when you work with means. Okay, so normally at this point, what I would do is I would hand out a bunch of dice to y'all, and we would roll them again and again and again in an experiment. And so what instead, I think it's interesting for you guys to see how a simulation is made to do something that's equivalent to a bunch of us rolling dice. So I'm going to make a simulation in Excel, trying to explain how it works. And we're going to just show what a distribution of averages looks like. Okay, so right now it's asking a question, what's the mean roll on a 6-sided die? Okay, so the mean, this would be a population mean because there's 6 sides and no more. And the mean, you could just average 1 through 6, assuming they're all equally likely. Okay, so you would just do 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. And I think you're going to get 3.5. Okay, so we know the mean. The standard deviation maybe is a little bit harder. So maybe we just do that in Desmos. Hang on, let's pop over there real quick. Okay, so I'll share this. Just to remind you, if you ever need a standard deviation from Desmos, you put a P after the standard deviation formula. So here are the rolls on my die. I'm assuming they're all equally likely as I do this. If they're not all equally likely, that changes all your statistics. It changes the average. So there's the mean, 3.5. It changes the standard deviation as well. If it's a fair die, then this is a good standard deviation. Again, for a population standard deviation, we say STDEV with a P at the end of it to stand for the population standard deviation. And this is a population of all rolls on a die, so this is all good. There it is, 1.7078. Remember, variance is a lot cleaner than that, so I'm going to square that standard deviation to see what the variance is. There it is, 2.9167. I'm going to be pretty precise with this. Okay, so let me go back to my iPad real quick. Okay, so the standard, hang on. Okay, so standard deviation was, what did we say? 1.7078. Okay, with X being the roll on the die, so I'll just say die roll. The variance of X is sigma squared. So that's going to be 2.9167. And the distribution shape, well, just to make sure we're all on board, it assumes all outcomes are equally likely, and that's what we mean by a fair die. And if that's the case, then all the probabilities are the same. They should all be a sixth. So I'm just chopping this up a little here. So this is called a uniform distribution when all the probabilities are the same. So those are X, and I'll just put 1/6 inside of each of these. And the only thing here that's maybe recognizable is the mean is in the center right there at 3.5. So mu is 3.5. All right, any questions yet? Okay, so let me look at my chat real quick, make sure we're good there. Think we're good. All right, so I think again, to just do a quick little thing, was I'm supposed to give you 4 dice and compute the mean roll. Okay. And I'm gonna do this a whole bunch of times. And the results are just gonna keep changing every time I do it. So just be a little patient here as it's gonna take just a little while to put all this in. Let me share my, I'm doing this in Excel, which is probably what I'm most familiar with for stuff like this. So all I'm going to do is just pick a random number between 1 and 6, and that's the roll of my die. So rand between is the command, and 1, 6 are the arguments for the command to tell it to pick a random number between 1 and 6. I hit the enter key and it rolls the die. I actually want to roll 4 dice, so I'm going to copy that number or that formula over 4 times. Okay, and then I want to compute the mean. And notice when I hit enter, these will re-randomize. So every time I enter something, it shuffles the deck or it rolls the dice again. So this mean's just going to keep changing. So I'll just say equals average for the mean. And then I just take the average of these 4 numbers like that. Okay. So this tank coming out is 3.25 this time, which is close to the population mean. Remember, the population mean is 3.5, but the sample mean is coming out as 3.25, and it should be close, right? But sometimes you'll get weird outcomes. I think I want to do this maybe 500 times. So I'm going to copy my work here down to row 501, I guess. So right there, I've rolled 4 dice 501 times. And so this list goes on and on and on. And I'm going to go back to the top. What I really want to do here is to compute the mean of all these. So these are my rolls. So maybe I'll just do a little, I don't see the button I'm looking for. Oh, here it is. Okay, so then let's get our averages. I'm just going to drag that, the average formula down, and it'll just do the reference all the way down to the bottom. To 501 right there. Okay, so a whole bunch of different averages from the roll of 4 dice. Okay, now what I need to do is somehow tally all of this. So what I'm going to do is make a frequency table. And so let's do it here. Again, this is going to keep changing every time I do it. So just get used to that. Okay, so I guess I should say frequency table here. And then maybe a value for X and then frequency. Okay, so my X is, I think the smallest I could get is I could get an average of 1. Probably won't happen. That would mean I'd have to get a 1, I'd have to roll 4 ones to get an average of 1. So that's probably not going to happen. These are going to go up into quarters because when you compute the mean of 4 things, you're dividing by 4, which is 1 divided by 4 is 0.25. So these have to go up in increments of 0.25. So the next one I'm going to put in is 1.25, like that. And then I'm going to just drag this down until it goes up to 6. That's the highest average I could get. If I roll 4 6s, I'd get an average roll of a 6. And then for the frequencies, what I have to do is I have to use a command called count if. Okay, I want it to count all the numbers in this range, so I have to drag across that. There's probably better, I know there's a better way to do this, but here we go. Slow down right there. Okay, all of those. And I'm going to do a comma. Maybe I'll slide back up to the top here. So count the numbers in that range if they are equal to a 1. Hit enter. And you can see that 1 occurred 0 times. Again, that means, again, I rolled 4 ones, and so the average was a 1. Never happened. If I do this again and again, eventually it'll happen, but it's again, that's a rare event. I have a little adjustment I'm going to do to the formula to make it the reference what they call absolute. So pardon me while I do something strange. It puts dollar signs. Ooh, I need dollar signs everywhere. Here we go. All right. Now I'm just going to copy this down so it does the count for every number here. So you see we got no 6s either. To get an average of 6, you'd have to roll 4 6s. That happens 0 times. And 1 happens 0 times. You see easily the most common occurrence is a 3.5, which is the population mean. You can also see that these numbers kind of go down sort of symmetrically on both sides. That thing is just begging to be a bell-shaped distribution. So let me do a quick histogram of the frequencies. I have to remember how to do it. Just a bar graph, I think. Yeah, just a plain simple bar graph is what I'm going to do. Come on, it's working. There's my bar graph. It's not great. Oops, did not mean to do that. I think I'll delete that though. Okay. Yeah, it's not great. I'm going to just tweak it a little. Make it look like a histogram by making the gaps between the bars 0. And then I think I'm interested in fixing the labels at the bottom. So select data, my x-axis labels, I want to be these guys. So that'll finish it off for me. Okay, so that's a nice little histogram. And you see it's sort of bell-shaped, it's not perfect. Okay, I can reshuffle this until I get one that I really like. So that if I ask it to re-randomize, it'll just keep redoing this. I like this, sort of like that one, it's sort of skewed. Hey, if any of you guys has questions, will you just say it out loud or type something in if you like? Can you see how we're going to be basically saying that means from samples have bell-shaped distributions? That's a good one. I like that one. Now, there's a rule about how big the sample size should be. I've got samples of size 4 here, and I did 1,000, I think, samples of size 4. Okay, you can see the mean is of the sample means is 3.5, which was the population mean. Okay, so we've got center, we've got shape. The center is the same average as the population, 3.5. The shape, these guys want to have a bell-shaped distribution, and if you think about it, it totally makes sense. The average roll on a die is 3.5. So if you roll 4 dice, you expect the average to be close to 3.5. Not always, okay? But mostly this should get pulled toward 3.5. And you can see the bulk of these are pulled toward the 3.5. That's why they move to the middle. Averages move to the middle. Okay, totally makes sense. It's really hard to get extreme averages. Again, to get a 6, you'd have to roll 4 6s in one shot. That almost never happens. I do notice that we got 4 1s in one scenario here. I think it's the first time I've seen that, where we got an average of 1. Okay, it had happened one time in 1,000, and maybe the 10th time I've done this, I finally got one. Okay, but the point is it's very rare, and the probability is very low for the extreme values, which is just like a bell curve. Okay, any questions? Okay, so unfortunately we have to copy these down. So I'm gonna have this up as I paste all these values in. And when it asks for the averages and stuff, actually I'm gonna do a couple things real quick. I'm gonna paste, I'm gonna do what they call a paste of my values here, because I don't want these to change anymore. So I just copied that table. Actually, let me get the whole thing. Every time I do something, the values change. So I want to freeze them. So when I do my paste right now, I'm going to do what they call paste special. And I'm going to have it paste not the formulas, but the actual values that were computed. So that's the distribution we got. And this distribution is going to keep changing up here. So we'll just kind of forget about it now. And see, at some point, I'm going to need the mean and the standard deviation of these values. So we'll do that in a second. I said X up here, but these are really sample means, so it should say X bar. Okay. All right, so let's go back to our notes, and then I don't know if I'll come back to the Excel spreadsheet. What I am going to do is just paste over the results that we got. Okay, so let me get back to the iPad real quick here. This looks a little tedious. I think we'll skip the tally. What do you say? If you get bored, you can put in a tally. In Excel, we just got the actual frequencies and skip that. So I'll just tell you what the frequencies were. One, 1, 2, 6, 11, 25. 35, 40, 54. 59, 53, 51. Oops. Um, 56, 34, 28. Um, 20, 11, 9. And 3, 1, 0. Now I think there were 1,000 values here. Let me just double check, make sure I had 1,000 of them. So I'm just totaling up the frequencies right now. Yeah, there was 500. Okay, so the total here was we did 500 samples of size 4. Okay, any questions about those numbers? Do you need more time with that, anybody?
I do, just like another quick, like 30 seconds.
Yeah, I'll give you 30 seconds. Just let me know when you're good.
I'm good.
Okay, thanks. We have to, oh, actually, we're not going anywhere, are we? We have to do the relative frequencies. So if you think about it, 1 out of 500 is actually 2 out of 1,000. So I think that first relative frequency is 0.002. Essentially 0. 1 divided by 500 is 0.002. So it's sort of like multiplying it by 2 and putting a couple of zeros in front of it. I'm going to do that on all these. Multiply 2 by 2 and put a couple of zeros in front of it. I think 2 out of 500 is 0.004. 6 out of 500 would be 0.012. 11 would be 0.022. 25 would be 0.050. That's a 5% chance. 35 better be 0.070, right? 40 better be 0.080. 54 point what? 0.108, I guess. Okay, any questions? All right, well, then we keep going. 0.118. I think this one will be 0.106, 0.102, 0.112, 0.068, I guess. 28. So what's that? 56.056, 0.040, 0.022, 0.018, 0.006, 0.002, and 0. Okay, so those are our relative frequencies. And you can see the horrible thing I'm about to do. I think I'll start in the middle. So if I did the 3.5, that's got a 0.106. I'll just try and set that down. 106, gonna be right here-ish. And I'm just going to be working with bars on both sides of that. So on the right, 375 got 102, very similar height. Well, these are going to be hard to distinguish. Oh, God. So next one, I had a 102. Now I have a 112. So that's actually the highest one. And then a 068, 056. 068 is almost 07. 068, 056. I think I screwed up on one though. I'll fix it in a sec. This 068 is too high. 05, 6, 7, about there. Okay, and then 040, 022. One eight. Oh, 006, 002. So 006 is just so tiny. And then 002 is going to be almost indistinguishable from 0. So I'm just going to sort of turn this into a bit of a line here at the bottom. Okay, and then on the other side of 3.25, I got to do a 0.118. And then a 0.108. There maybe. And then a 0.080. And then a 0.070. Okay. 050. Then 022. And 012. Getting almost too hard to do again. Um, 0.004. I'll do my best. Maybe like that. And then the last two will just basically be lines. So I think I'm just going to draw green lines for the last two. A thick green line, maybe. And same with this one over here. Okay, so there's our histogram. And then obviously the question is always about center shape and spread. Okay, and this is a distribution of sample means. So let's label it as such. This should have an X bar label. Sample mean is a mean X bar. Okay, so obviously this is a bell shape. Any questions? Now we can see the mean sort of here. Is it gonna be around 3.5? Looks pretty darn close to 3.5. But I'd like to get an exact figure for this. Okay, so I'm just gonna go over to Excel and let's see, there's a couple of different ways to get the mean. We could do it straight from the list of sample proportions. So I think that's what I'll do. So I'm gonna pop over to Excel again. And just remember that the sample means here, these are the X bars. Oh no, except for they've changed. So I can't do that. I'm gonna have to do this from the frequency table down here. So the frequencies, you know, if I call the X bar values, I'm just gonna call X for a moment. And the frequencies we'll call F. And just to remind you, when you do a standard deviation, you have to do a mean, you have to do the sum of fx over n. The standard deviation requires an fx squared. Let me see, how do I do this? I know what to do. Hang on, I changed my plan all of a sudden. I'm going to put in the relative frequencies that we did a minute ago. And I'll just, relative frequencies, I'll call P of X for probabilities. And so then I'll just do what we did by hand, where you take the frequency and you divide by 500. So these are the relative frequencies we got. Okay. And then to get the mean, I'll do the sum of X times P of X, which is another way to do it. And the standard deviation, you need an X squared times P of X, like that. So let me go ahead and do equals X times P of X goes there. And I just need to add those up. So I'll put the total down here, and this will be the mean. So it's 3.472. It should be close to 3.5, and it is close to 3.5. And then X squared P of X is used to compute the standard deviation. So that's equal to the X squared times P of X, which is there. Okay, so I think I got that right. X squared P of X, yeah. So the total of that is that 12.73. Okay, so the rest of this, we can just go back to our notes and put in these results. So let me do my share back to that. Okay, so hang on. Okay, so the mean of the distribution is, I'm going to write in, I'm not going to use the Greek letter yet. The mean is the sum of X. I'm going to say these values are actually X bar times P of X bar. Okay, to use the right formula in the notes. And that came out to 3.472 or something like that. Let me double check. 3.472. Which is approximately 3.5. And that's the population mean. Okay, so the mean of the sample means I want to call mu with a little X bar next to it. The mean of the sample means, but 3.5 is the population mean, mu. So our point is to recognize that when you do sample means from many samples, you're getting these bell-shaped distributions, but also that the mean of the sample means, about 3.5, is the same as the mean roll on one die, also 3.5. Okay, any questions about that? In the long run, this would exactly make its way to 3.5. Okay, in a short run with 500 trials, it'll have some margin for error, as statistics always do. Okay, any questions?
Yeah, sorry, I missed. What would be the numerical value for P in the equation? I'm just curious.
When you say P, do you mean P, this right here?
Yeah, I was a
That's
little
the P of X. So that's the probability. So these relative frequencies, remember the values we have here are the sample means. Those are X bar, and there are many of them. Okay. One way to compute a mean of a list of numbers is to multiply by probabilities. Just to remind you, relative frequencies are estimates of probabilities. So when we say P of X bar, we mean the probability of rolling a one, sorry, of getting an average of one from rolling 4 dice is about 0.002 based on a relative frequency. So the probability, that just means the probability of the X bar, which was 1 on this one. Okay, so
Okay.
you're taking each value, multiplying it by its probability and adding that up. So that's what this says. Take each X bar, multiply by its probability that we estimated with a relative frequency, and add those up. And that's what I did in Excel. And it came out to 3.472, which is not exactly 3.5, but in the long run, it would be. Okay. You okay?
Okay, thank you.
And then the standard deviation has its own formula. Now, again, the standard deviation formula from a probability distribution was this. It was the sum of X squared times its probability, P of X, minus the mean squared, okay? But we're working with sample means, so I'm gonna say sum of X bar squared, P of X bar, minus the mean of X bar squared, like that. Okay, and so this we'll call a standard deviation of X bar. Okay, so we did all these computations in Excel. The sum of X bar squared times P of X was 12.73625. I'm probably being too precise. 12.73625. And if we want to subtract the square of the mean was 3.472, and we would square that. Okay. So this is a bit of an ugly computation on a calculator or in Desmos. Start with the square root symbol and then fill it in. And if someone would just kind of let me know what you get.
I got 0.82551.
Yeah, let's go with 826. Okay, so that's a lot of work. We worked really hard to get the mean of all the sample means. And the fact is that we won't have to, because the mean of all the sample means, which all this work we did, was the same as the population mean. So we'll know, in advance what the mean of the sample means would be. It's the same as the population mean. Okay, so you don't actually have to do all the sample means to know the mean of all the sample means. It'll be the same as the mean from the population. Standard error or standard deviation, a lot of work to get to that. And what we'd like is some formula that will predict that as well. Okay, so I just want to remind you a couple of things. I'm just going to go through the development of the formulas. Just a quick reminder, if you do the expected value of X plus Y, this is the expected value of X plus the expected value of Y. Same for variance. The variance of X plus Y is the variance of X plus the variance of Y. So the expected value of a sum is the sum of the expected values, and the variance of a sum is the sum of the variances. Also, if you multiply by a value, the expected value of any number times a variable x that changes, the constant, which I'm calling k, could come out of the expected value. So you do k times the expected value of x. Variance is a little different. When you do the variance of any constant, k, times a variable x, the k comes out. Does anybody remember how the k comes out? Okay, it comes out squared. So you're going to have k squared times the variance of x here, like that. So if we want to do the mean of sample means, you're going to go this route. Okay, so for the population mean here is mu. The population standard deviation is sigma. While I'm thinking of it, I want to back up, I'm so sorry, and say that mu is the same thing as the expected value. So the population mean is also denoted E of x, the expected value of the variable x. And the variance of x is sigma squared. Okay, so that's just to remind you of the notations. Okay, here's the expected value of sample means. So if I do the mean of sample means, that's what we had up here. We think it's the same as the population mean, but I want to do a long run mean, not just from 500 samples. Okay, so what I have to do is I have to take the expected value of sample means, like that. And sample means are computed with a formula. So I would take the expected value of whatever the formula says, which is the sum of each x in our sample divided by the sample size, like that. Sample size is a constant. It does not vary, not like the values in the sample that vary. So when I look at that n down here, that's just like a k, a constant that doesn't change as you compute your mean of all the variable values of x. Okay. The point is n's a constant and constants can come out. Technically it's a 1 over n. So we would write this as 1 over n expected value. Oh, my bad. 1 over n expected value of the sum of all the different variable values of x. Okay. And then the next thing you need to remember is that the expected value of a sum is the sum of individual expected values. So I can add inside the expected value, or I can add outside the expected value, which gives me excuse to write it this way: 1 over n times the sum of the expected values of each value of the random variable of x. But you know up here that the expected value of the random variable x is mu. So I can change this to 1 over n times the sum of a bunch of means, mu. And then the question is, well, how many means am I adding together? Well, you have to remember that when you compute x bar here, you're adding n values of x together. So this sum is adding n things together. If you add the mean to itself n times, you get n times the mean. So this is just 1 over n times the mean, which is the population mean. So what this says is that when you compute the mean of all sample means drawn from a population, you get the population's mean. which is basically what we saw. The mean of all the sample means came in at 3.5-ish, which is the mean roll on a die. Okay, it wasn't exactly 3.5, but in the long run, it does go to 3.5. Any questions? And this is the mathematical proof for that. So I already kind of knew this. I knew that it was going to come out to 3.5 because we saw it coming out to basically 3.5. Any questions? What's not clear and what is never clear is the standard error, the standard deviation of the sample means. So here, we definitely need to figure out how we're going to get the standard deviation of all the sample means without looking at all the sample means, which is what we did up above, right? We did 500 sample means and we got a standard deviation. A lot of work. All right, well, let's see if we can do that. Standard deviation does not have nice properties, so we always work with variance. So let's start by talking about the variance of sample means. That would be sigma x bar squared. So it's the square of the standard deviation of the sample means. So I'll just write it in words here. This is var of sample means. Okay, but now we just play the same game that we did with the expected value. The variance of sample means is the variance of whatever a sample mean is, which is the sum of each x divided by n. Okay. And then remember, the n is just a constant that does not vary as x varies. Okay, so constants can come out, but not the same way. Remember, the variance of k times x is k squared times the variance of x. So that 1 over n is going to come out as a 1 over n squared. Like that. And then you have the variance of the sum. Like that. But as it says in the properties, the variance of a sum is the sum of the variances. So you can add inside the variables inside the variance, or you can add outside of the variances. So I'll move the sum outside of the variance. I'll say this is 1 over n squared times the sum of the variances of x. So I'll write sum var of each value of x. Remember, those are varying, so the values of x are all different. Okay, and it varies. So the variance of each one of those, as you know, we're doing the sum of the variance of each value of x, and that's up here. The variance of x is sigma squared. Okay, so I'm summing a bunch of sigma squared variances together. And again, how many am I adding? Well, again, to compute x bar, you're adding n values of x. So this sum is adding n times. You're adding the variance to get to itself n times. So you get n times the variance. So this is 1 over n squared times n times the variance. Like that. And then we get a cancellation. 1 factor of n in the numerator, you can write it this way, n sigma squared over n squared. So you get 1 factor of n in the numerator. 2 of them in the denominator will cancel 1. So we'll have this as sigma squared over n. So that's the variance of sample means. And standard deviation of sample means is the square root of the variance. So let me draw a line. Okay, so Sigma X bar is the standard error or standard deviation of X bar values. Remember, we need standard error so we can compute margins of error. Remember, 95% of a normal distribution is within 2 standard deviations of the mean. So 95% of the time, a sample mean is within 2 standard errors of the population mean. That's why we use about 2 standard errors for our margin for error. And that's why it's so important that we know what the standard error is in a sample mean so that we can double it and make a margin for error. Okay, any questions? Well, this is easy. This is just the square root of the variance of X bar. Or if you like, I could write the square root of sigma X bar squared. Now, that turned out to be the square root of this result at the bottom. That was sigma squared over n. Oops. So the square root of sigma squared over n. Square roots can break up this way, square root of sigma squared over the square root of n. And sigma squared, the square root of that better just be sigma. Those undo each other. So this is just sigma over the square root of n. So that's the standard error for sample means. And where do you use standard errors? Again, you use standard errors to compute margins for error. But also a standard error is a standard deviation. So if you're going to take a z-score of a sample mean, you need to divide by the standard error when you take a z-score. So we'll need that there as well. Okay, let me just make a note here. The mu X bar here is the mean of all sample means. Okay, so the mean of all sample means is the mean of the population you're sampling from. Standard error is sigma over the square root of n, where sigma is the standard deviation of that population. Is it time for our break? I think it's well overdue, right? Yeah, so let's do our break till 10:25. And I'll see you guys in a few minutes. I did pick up, just to let you guys know, Caitlin, I got you. Laura's gone, so that's interesting. Caitlin, you're marked here on the attendance, so we're all good. I'll talk to you guys in a little bit. All right, you guys, I'm back. Hope you're back. Just real quick here. Did Laura Barasa, is she here? Okay, so let me just keep going here. So we've got a formula for the standard error. Let's see what comes up next here. We need to see if this works. So I don't think I stopped the recording, so let me double check that, make sure this is still recording. Yeah, it's still going. We're good. Okay, so let's check to see if it works. Actually, let me verify that it's down here. Yeah, actually, we will do that down below. Okay, so I'll erase that. Okay, so just real quick, I want to go ahead and summarize everything that we came up with. It's a lot of work, but obviously we want to say that means from samples have bell-shaped distributions. We also, and again, it's all about center, shape, and spread before we can really understand it. So the shape we've got, we thought the mean of sample means was equal to the population mean that we're sampling from. That turns out to be theoretically true, and it's true in the long run in practical scenarios as well. And now we've got that, so that's center, shape we've got, spread is the standard error. So we can summarize all of this. By the way, there's a rule about how big your sample needs to be. This is bell-shaped, but it's not as normal as it could be. It turns out to be just absolutely really normal if you can get your sample sizes up bigger than 30. That's a rule of thumb that statisticians have come up with. And so I'm going to add that to this theorem that we're about to put down. Whenever we say central limit in statistics, we're talking about a statistic that tends toward normality in the long run. So the given is a population of values X with mean mu. Oops. And standard deviation sigma. Consider the sampling distribution. Now, sampling distribution is just a distribution of a statistic from a sample. So the title of the lesson is sampling distribution of sample means. So that's what we're studying right now. Consider the sampling distribution of all sample means X bar from samples of size n. Okay. The following can be proven. Oh, let's put this down first. The sampling distribution has mean, this is the mean of sample mean, so mu with a little X bar subscript, and standard error. And we call it standard error when it's the standard deviation of a statistic. The statistic is X bar, and the standard deviation is the standard error sigma X bar. Okay. And the following, some of this we have proven, and some of it is too hard to prove. But the following can be proven. The hardest thing to prove is that sample means will always approach normality. It requires a fair amount of calculus. and advanced statistics to prove it. But the first one is the sampling distribution is approximately normal. Oops. If either your sample size is bigger than 30, and you can have small sample sizes smaller than 30 if your population is normal. So if n is 30 or the original population is normal, not the population of sample means, but the population you're sampling from. So the original population is normal. One of those has to be true. And so you'll see us asking if the conditions are met or the criteria are met. Either one, they don't have to both be met. Okay. Secondly, the mean of sample means is the mean of the population you're sampling from. Okay. And the third has a sort of a stipulation. The standard deviation of sample means. Let me just go. I want to back up 1 second. I just remembered I'm supposed to put something down that I forgot to put down. So this rule back here about the variance of a sum being the sum of the variances, this assumes the variables are independent, which means one does not affect the other. Okay, assumes X and Y are independent. Okay, now this is a little different for the sample means, and so I'll update that language in a second from independent. Okay, assumes X and Y are independent. Okay. And in this argument about the variance of the sum being the sum of the variance, that's right here, variance of the sum is the sum of the variances. That's where I'm using this. And that's only true if those samples are independent. Now, if you're talking about a bunch of different values of X that you're randomly selecting, the only way one value of X can affect the next random value of X is if you're not replacing values when you sample them. So the assumption is that we're sampling with replacement. So I'm just going to go down here. This will all be independent if we sample with replacement. So here, sigma X bar is sigma, sigma over the square root of n if we are sampling with replacement. Otherwise, it's a little different if you're not. There's still a way to do it, but it's kind of it's a little more complicated, and we won't cover that. So we assume we're just sampling with replacement. Okay, any questions about this? All right, well, then we want to see if our values match. So the mean of sample means was, I think, 3.4, I don't remember, 472, which was approximately 3.5. And that's the population mean. So I'll just say close enough. Okay, any questions? So the mean of the sample means was basically the mean of the population. And that will be true in the long run, as I've said. What we haven't checked is the standard deviation of sample means. So the standard deviation of sample means of all of them, long run standard deviation would be the population standard deviation over the square root of sample size. So we have to go back, way back to find the population standard deviation. So way up at the top. That was this thing, 1.7078, the standard deviation of the 6 rolls on the die, assuming they're all equally likely. Okay, 1.7078. Okay, and we divide by the square root of the sample size. Now the sample size was each individual sample where I dropped the 4 dice, in my simulation. There were 4 dice, so N was 4 every time we did it. Okay, any questions about that? Of course, the square root of 4 is 2. So this is just 1.7078 divided by 2. Anybody, what's that? Anybody?
Point 8539.
Thank you. So, and notice back here, we got 826. So this was the theory, this is the actually us doing it with a simulation, 0.826. The theory says we should get closer to 0.854, I'll say. So this is technically 0.854. This is the correct long run value. Okay, now this is close again to the 0.82. What did we get again? 826, which was from the simulation. So there's no mistakes here, but the simulation can't know the long run. I think we're just sort of comforted again to know that this is really close. Again, it's close enough. So we can determine the standard error using this theoretical formula. And actually the theoretical formula is more precise than using a simulation like this. Simulations, you never know how they're going to run. Okay, any questions? And other simulations would come out even closer. Okay, so is there any question? Now, for the margin for error, this is just straight as before. So previously, the margin of error was just Z alpha over 2 times the standard error. Okay. And the only thing that's changed is we're working with a different statistic now. It assumes that the statistic has a normal distribution. That's what that Z-score is. It's from the normal distribution. So let's just say it assumes X bar is normally distributed. I'll just say normal in distribution. And we have a guarantee that that will happen as long as your sample size is bigger than 30 up here, or that you're sampling from a population that's normal. So there's 2 ways you can pull that off. Okay. And then you can use these Z-scores. Remember, the Z-score is about 2. We're saying margin of error is 2 standard errors, which is just going to work 95% of the time. That is the empirical rule. 95% of values are within 2 standard deviations of the mean. It is the empirical rule. So we must, but the empirical rule only applies to normal populations. If the population is not normal, then you don't know how far out you have to go to capture 95%. And so this only works for bell-shaped distributions. That's why we'll always say, well, you better check that you've got at least 30, right? At least 30 in your sample, or that you're sampling from a normal population. Okay. So, and the standard error now, this is a Z alpha over 2. Standard error is sigma over the square root of n. Okay, and that's that. Pretty straightforward. Okay, any questions? All of that theory, this is actually super simple, okay, to get your margin for error. And you can also do z-scores using this. So just if you need a z-score, let's put this in here just for future reference. If we need a z-score from an x bar value, remember z is just always value minus mean over standard deviation. Okay, so the value is x bar. And the mean of x bar values is the population mean that you're sampling from. And the standard deviation of x bar values is the standard error. So you would use sigma over the square root of n, like that. Okay, any questions here?
Could you zoom out a little?
Oh, yeah. Is that good enough?
Yeah, thank you.
You bet. And so this is where you'll be able to say, hey, this sample mean is statistically significant because it's more than 2 standard deviations from the population mean. And when you're able to measure how far a statistic is from a sample, from a population mean, then you can test how significant a value is, which is the essence of what we call a hypothesis test. And we'll start doing those in the next chapter. All right, any questions? Are we good, or do I need to stay zoomed out here?
I think we're good.
You sure? Okay. So all that's left here is to do our confidence intervals. So, and that's super easy. And the confidence intervals, just exactly what we were doing with the proportions. And you just kind of put it all in context. So the confidence interval we did before was for proportions, which is a p hat. You get the margin of error for a p hat value. And now we're doing means. We still want a margin for error, but it's a different kind of statistic. So this statistic has a different formula for the standard error, and that affects the formula for the margin for error. It's basically the same though, okay? Any questions? If you can do one, you can do them all. You just need to know the formula for the standard error. All right, well, let's go ahead and I think we can just put this together here. So let's just read it. It says, and this is 6.5, it's confidence intervals for the population mean. When sigma is known, the population standard deviation is part of the formula for the standard error right there. What's the odds you're going to know the population standard deviation? Basically 0. Okay, so this is a huge caveat here. When sigma is known, that's not going to ever happen. But we're still going to do this because it's a step towards the problem when sigma is unknown. You don't know population parameters ever. You have sample statistics that estimate them, but it gets a little more complicated when we use a sample standard deviation. So we'll deal with that in the next section. Okay, so I think we just real quickly pound this out. That what you have to gather for one of these, let me just read this again. In this lesson, we learned to do a confidence interval for a population mean when the population standard deviation is known. This uses an estimate of the sample, mean, x bar, and its margin of error. The steps for the confidence interval are as follows. So you have to gather the statistics you need. So you'll need x bar, you'll need n, You'll need sigma, which is the unfortunate part. This is the population standard deviation. Nobody's surveying whole populations. Okay. You'll need the level of confidence. You'll maybe compute alpha is 1 minus the confidence level. Okay. There's also a check in this step. So this is actually a gather and check here. The formula for the margin of error uses the empirical rule basically, and the empirical rule only applies to normal populations, and sample means are only normal if your sample size is bigger than 30, or if your sample means are coming from a normal population itself. Okay, so you need to check that N is greater than 30, or the population you're sampling from is normal. Okay, any questions? Okay, so that's all you got to do. The lookup is the Z alpha over 2. Okay, so easiest place to do that is table A2. And this is just as you did before, so this is not new. For table A2, let me draw the picture of this too. So basically alpha over 2 is the area of a tail. Okay, the area in between these z-scores is the confidence level. So that's why we're doing 1 minus the confidence level. So this is the confidence level. And again, alpha is 1 minus that. Each tail is alpha over 2, so the tails together are alpha. But the table wants the area to the left of the z-score. So the area to the right of the z-score here is alpha over 2. The area to the left would be 1 minus that. So you're searching for something approximately equal to the complement of the right tail. So 1 minus alpha over 2, like that. And then in table, this is table A1. I'm sorry, you guys. So again, table A1, and then you go out to the edge of the table, you see that Z alpha over 2. Oops, so I'm gonna write it correctly. Z alpha over 2, and then you go up to the 100th place. Okay, I'll show that in a sec. I hate using table A1 personally. So what we'll also put up is table A2, just as a reminder of how this works. You just look up your alpha and make it sure it says 2 tail. Okay. Degrees of freedom don't apply for the normal distribution. So you go down, sorry, they don't apply for the normal distribution. So you go to the bottom row where it says large degrees of freedom. You learn what degrees of freedom again are soon. But the large Z business is in the bottom row. Always go to the bottom row for Z scores. And then you just go down under your alpha value here. It's super easy, and it'll give you the Z alpha over 2 directly with 3 places after the decimal. So that's preferred to table A1, which only goes 2 places to the nearest 100th. Okay, so I recommend you use table A2. Then for the margin of error, we know what to do there. That's E equals the ZF over 2 that you just looked up. That'll always be around 2, but it's really precise. Z alpha over 2 standard error. So that's sigma over the square root of n. Okay, so the endpoints of the confidence interval are just the estimate, which is now x bar plus or minus your margin for error, which means in the interval notation, we would write x bar minus the margin for error is less than the population mean is less than x bar plus the margin for error. Okay, any questions? And it's the same thing here. You just say we are this confident that the mean is between these two values. Okay. The population mean. Okay, so we are blank percent confident that the population mean of whatever population is between blank and blank is the idea. Okay, and you're not going to use exactly that wording because it just depends, on how they ask the question. So that's the idea. We just talk about how confident we are. We don't say that it's a 95% probability because that's not really how probability works. This is either a true or false statement. It's not a probability statement. So we don't like to say, oh, the probability is this. It's either it is or it isn't. But we will say sometimes, well, what I mean is 95% of the time I'll be right. Hopefully this is one of those times. Okay. Any questions? Okay, so that's it. We can do a quick little example here. This is super easy. So our first step was the gathering step. So you can see the X, let's see, let me just read it here. 75 adult men are gathered randomly and their mean height is 68.5 inches with an assumed population standard deviation of 2.7 inches. Okay, and it says give a 94% confidence interval for the mean height of all adult males. Okay, so let's see, who wants 94%? Nobody does, but there it is. Okay, so the gathering step, we need our X bar. Does anybody see that? That would be the mean from the sample.
That's 68.5 inches.
Very good, 68.5. Do we have a sample standard deviation or a population standard deviation?
Population.
Yeah, it says population standard deviation, so that's sigma. Okay, we'll use S for the sample standard deviation later. So sigma is 2.7. Okay, our N, anybody see that?
$75.
Yep. And the level of confidence is 0.94. So our alpha is 1 minus 0.94. And then the check is, remember, N is supposed to be bigger than 30. So yeah, N is 75, which is greater than 30. And that's all you need to write here. Any questions? So we don't care. The distribution of the population is irrelevant. Yeah, I just kind of want to remind you something real quick. Even when you're sampling from a non-normal population, where was it? Here. We'd look at the population of rolls on a die. If it's a fair die, then it's a perfectly flat distribution here. They all have, meaning all outcomes have the same probability. So even when you're working with a population that has a non-bell shape, okay, the means from that population will be bell-shaped. So that's the important thing of statistics. You don't need a normal population to have a distribution of sample means that are normal. That's the importance of the normal distribution. It doesn't matter if you're working with normal populations. Your statistics, like the means that you compute, will be normal. And that allows us to do all kinds of things when we study means, okay? Will they always be normal? No. Again, the rule is your sample size needs to be bigger than 30, and that's usually strong enough to guarantee it. Or you're sampling from a normal population. So there's two ways to make that happen. It's not a big deal to get more than 30 in a sample. Okay, let's see here. We've done our check. N is bigger than 30. The second step is the Z alpha over 2. Okay, so if you do table, this is step 2 here. So if you do table A1, and you do 1 minus alpha over 2, this is 1 minus 0.04. Oh, I didn't do alpha. Alpha is 0.06, right? So 1 minus 0.06 divided by 2. What's that?
.03.
Yeah, 0.03. So just reminder, wait, no, but you have to do 1 minus that.
All right.
0.97.
Yeah, 0.97. Okay, so what's really happening here, just as a kind of a, gosh, I don't have a lot of space, but if you were to draw your bell curve, remember, you're just trying to find that positive Z-score. The area in the right tail is 0.03. That's the alpha over 2. The area to the left of that's 0.97. And that's why we're looking at 0.97 in the table. And so we go, I don't think you'll see a 0.97, but there'll be something really close. So let me bring that table up real quick. Okay, so this horrible thing. So we're doing 0.97, we said, right? So 9699 is just so close to that. And it's closer than 9706. Okay, so are you guys on board with what I've got here? So my Z-score is going to be 1.8, and remember the hundredths place 0.08, so you add those 1.88. So any questions? It's 1.88. Oops, I did not mean to do that, sorry. Okay, so it was in the table, it was a 9699, and the 9699 goes out to 1.8 and up to a 0.08. So that means our Z alpha over 2. I think I'll put this somewhere else, but it's 1.88. Okay, so that's a lot of work with table A1. Okay, any questions? Easier on table A2. And that's what I'm encouraging you to use. So for the degree of freedom, you just go down to the bottom row where it says large. Those are Z-scores in the bottom row. They're T distribution scores otherwise. We want Z. Our alpha, I think, was 0.06, right? Make sure you do the two-tail lookup. Oops. And I'll show that now. Obviously, it's going to say something close to 1.88, but maybe a little different. Okay, so let me find that one. It's hard to show because it's in the bottom row and I can only get so much on the screen here. But under two tails, it was a 0.06 alpha. So here I am. Okay, any questions here? So 0.06, now I'm going to the bottom row. All the way down where the z-scores are. And you can see, there it is, 1.881, same value, easier to find it this way. Just go to the bottom row under your alpha value. Okay, 1.881. Any questions there?
I have a question. I feel like I got confused. How did we find the? Oh, never mind. Just kidding. I see it. I was looking at where the alpha was, but I like looking right at it. The 1 minus 0.94. So all good.
Okay. Okay. And so then once you have that z-score, and we're going to go with the 1.881, then the rest this is just super easy. Let me box this in a little bit here. So for step 3, we can do that standard error now. So that would be z alpha over 2. So the only really thing that's tricky here is getting that z-score. And once you know how to do that, you're set. So the z-score is the 1.881. Again, it's always about 2 standard errors. But with lower levels of confidence, then that you go out fewer standard errors, but you're just less confident. Okay, 68, standard deviation is 2.7. And this is over the square root of our sample size, which is 75. So let's see if we can agree on that. Just shout it out when you get it.
I got 0.586.
That's great. And I'm actually going to say, because if you look at our numbers here, the mean only has one place after the decimal. Same with the standard deviation. So I think I'm going to go, I don't want to get too ridiculous about how precise it is. But normally with means, we do one place more than what they give us. So I think that's what we'll follow here. And just to keep in mind, proportions, the rule was 3 significant figures. But with means, we do one place more than the data they give us. So our mean is 68.5. My margin of error, I'm going to do 2 places, so 0.59. Does that make sense, you guys? That's a pretty small margin for error. And then step 4, we would do the endpoints of the interval. So remember, it's x bar minus e and x bar plus e. Okay, so our x bar was the 68.5. We're just adding and subtracting the margin of error. So we get 67.91 for the lower limit. And we get an upper limit.
59.09.
Fantastic. 69.09. And then you just say the male height we think is between these two numbers. Don't know for sure. That's it. 94% confident. That's it. Just like that. Easy. Questions? There's another one here just for practice. So I'm going to go ahead and read this. Okay, so it says the mean final exam score from a random selection of 250 of my statistics students is 76.5 points with an assumed population standard deviation of 12 points. Again, there's no way in the world you're going to know a population standard deviation, but give the 99% confidence interval for the population mean score of all students who take the test. Any questions? All right, so I'm just going to go through these steps again. The first step is just to gather all this data. So step one, the sample mean was 76.5. My N is 250. Now again, they say population standard deviation here, which is sigma, not S. S is a sample standard deviation. We'll do that later. So S is 12. Oh, sorry, sigma is 12. It just said we didn't do that. Sigma is 12. Confidence level is 0.99. So alpha is 1 minus 0.99. So this is 0.01. Okay, we do have to do our check. So for the check, N has to be bigger than 30. Of course it is. N is 250, which is bigger than 30. So check. Any questions? So the second step is to get that z-score. So if you, let's just do 1 minus alpha over 2 real quick. So this would be 1 minus 0.01 divided by 2, which is 0.995. Okay. And so if you look at table A1, it's a little unfortunate. What it says is, if you look, there's a 9949 in the table, which is really close to 995. O, if you like, I'll put a no. There's also a 9951, and this is a perfect split between two z-scores. One of the z-scores is 2.57, so there's a 0.07 up here. And the other one is 2.576. So the next one's an 08. Okay, and there's an asterisk between these two in the table. So probably should look at that asterisk and see what that's talking about. Okay, so I'm going to pause for a sec before I go to the table just to let you guys catch up. So jumping down to the table here, just a reminder, we were looking for 9950 in the table. So, and there's different asterisks in the table, but the one I'm talking about is right here. Hang on. Okay, so right here, we're looking for 9950, and what you're seeing is a 9949 and a 9951. And again, these relate to 2.57 and 2.58. And what we really should do is try and find the value that goes between 2.57 and 2.58, since this is a perfect split. The natural guess would be 2.575, but it's a little more complicated than just averaging these. So the good news is at the bottom of the table, there's a little asterisk. All of these asterisks here refer to this down here, where it says if you're looking for 9950, you should use 2.576. which is it's between the two z-scores we were talking about, 2.57 and 2.58 is 2.576. So that's a lot of trouble, but you can see you've got these asterisks in the table that lead you down to this note. Any questions there? It's a lot of work using this table, and there's too much to think about, but let's go ahead and put that in here. So I'll put the asterisk between, and then the note for 0.9950, it says use z equals 2.576. So that's the hard table A1. Table A2, you do degrees of freedom on that one. Bottom row, large degree of freedom is a z distribution. Alpha is 0.01. Make sure it's two-tailed. Okay. And so we see when you go to that table, it's going to be the same. So let me pop that up. Okay, so here's the table. Remember, look this up under two tails and then go to the bottom row. So our alpha is 0.01, and under two tails, you're in the very first column there. Okay, so zipping down in the first column to the bottom row, it just says 2.576 there, which is exactly what we knew. Okay, any questions? So there's no asterisks, there's no, oh God, it's between two numbers. You just get the number here. So that's easier. Any questions? Oops, my bad, did not mean to do that. Any questions about that? Okay, so let's pop back here and put that in 2.576. That's our z alpha over 2. Okay, and I think we can finish this up pretty quickly now. So step 3 is our margin for error. So E is z sub alpha over 2 times sigma over the square root of n. So that's the 2.576 now. Sigma was 12. And you divide by the square root of n, which was square root of 250. Okay, so let's see what you guys get on that. So this is like 2.5 standard errors if you want to be 90%, 99% confident. Remember, more confidence requires a larger target to hit. So larger target means you have to allow a larger margin for error. And that's all you're doing when you increase your confidence. You're just enlarging your margin for error. It just gives you more margin, which makes you more confident. Okay. But it doesn't look as good with larger margins for error. And that's, again, just a trade-off. Just shout it out when you get it.
$1.96.
Perfect. And that's with 2 places after the decimal. Good. Because we started with 1 place after the decimal, now we're carrying 2 just to kind of add a little more precision. And then, so the 4th step is computing the endpoints for the confidence interval. Are there any questions? So we do X bar minus E and X bar plus E. Okay, so again, the X bar was the 76.5. Subtract the 1.96 and add. And if anybody gets either one of those, just shout it out.
$74.54.
Yep. And anybody else get that other one?
78.46.
Perfect. So we're just recognizing margin for error exists. There is error in every statistic, at least you should assume so. So when we report the results, we're basically padding this. We're saying, I don't really know what the population mean is, but I think it's between these 2 numbers. Right now, I'm 99% confident of it. But I did that by allowing a pretty larger, larger margin for error. So we are 99% confident that this is about a mean. So we'll just say the mean test score is between 74.54 and 78.46. What's that? Okay. I guess one of the things I like to do is write the interval down. So I am sorry for squeezing an interval. So wherever you can squeeze this in would be fine. But normally we like to write our interval down. So we would say that the mean, the population mean, which is unknown, we think is between 74.54 is less than the population mean, is less than 78.46. That'll only be true 99% of the time. Okay, any questions about that? Or about this conclusion? Yeah.
Earlier in the class, we talked about a homework problem where we had like a sample size of 900.
Yep.
And we were looking at like how the sample size affected our margins of error.
Yeah.
And it seemed like, you know, with a sample size of, we had sample sizes of like 900, and then we did like a couple with like more than 1,000, and we were getting, for like 98% confidence, we were getting margins of error like around 2%.
Yeah.
But here we have a much smaller sample size, and our margin of error is like 2.5%.
Right now, the only thing that you have to be careful of is that what I said was that when you work with proportions, a sample of size 1,000 usually results in a margin of error of about 3 percentage points. But those are proportions and percentages. This is means, and the weird thing, you know, with proportions, the standard deviations almost always come out about the same. There's not a lot of variability because with proportions, it's always between 0 and 100%. The values are constrained. Forget about 0 to 100%. Think about the fact that a proportion is always between 0 and 1.
Mm-hmm.
And having that constraint on the proportion really constrains the standard deviation. And so I'm able to say things like, well, the standard deviation is almost always the same. So the standard error is always the same, roughly, not exactly. And so the margins for error are almost always the same. And therefore I can say things like, with a sample of 1,000, the margin for error is always around 3 percentage points. That's because the standard deviation does not vary much. But here, these are not constrained values. You're just talking about the heights of people. What's the maximum height? There's not a maximum height, right? Or well, this one is actually almost like a percentage point. Oh, you got me. Oh God, yeah. I'm not thinking of these as percentages. I'm thinking of these as points. And all I can tell you is that in this context, in the context of means, the standard deviation is just a completely different computation here. Right. And so I don't want to, this is something else. Yeah, I'm gonna have to think, you totally got me because I did not see this coming, but this X bar here is not a proportion.
Yeah.
It's an average of a bunch of students' scores. And you have to remember a proportion is where you take the number of successes and you divide by a sample size. Completely different computation than this, where you're adding a bunch of quantitative values. So here the variable is quantitative. With proportions, it's categorical. It's just a different game. Mm-hmm. And so we have to remember the standard error formula is completely different. And so you just don't want to connect that discussion to this too closely. It's parallel, but the rules are just different when you work with means. Sometimes you get really huge margins for error with means because there's no limit on how big a standard deviation can be. Does that help?
Yeah, I think so. Yeah, I wasn't even thinking about that we'd switch to means. So, and I see how the standard deviation formula is different. Like before we were using the square root of PQ over N. Right. Now we're using, so I don't maybe you know, intuitively get it all, but at least I see that they're very different things.
Yeah, I think the main thing is you just have to keep that notion that proportions are always between 0 and 1. And here, a student's test score, well, even then, just like I said, it's a quantitative variable versus a categorical variable. It's just a completely different game. So I have to think there might be a connection here because these are still percentages, but I'm averaging a bunch of percentages rather than looking at just one percentage. So, which is what you do when you work with proportions. All right, so let's go ahead and do this issue. How are we doing for time? It's 11:25. I think we can squeeze all this in. Okay, so the managing error thing is just, again, we're solving for the sample size like we did at the beginning of class today. So the margin of error formula is is Z alpha over 2 times sigma over the square root of n. And what I'd like to do here is to pick my margin for error and determine what sample size would yield that margin for error. So again, I'm going to solve for the sample size here. So if I multiply both sides by the square root of n, and divide by the margin of error, then what happens is on the right, my square root of n cancels. And on the left, my margin of error cancels. So I end up with the square root of the sample size is equal to z sub alpha over 2 times sigma, and just divide it by the margin of error. And of course, we want to square that. So we're squaring both sides of this to get the sample size. Okay. And so that's pretty straightforward. It says your sample size needs to be, and again, this is a minimum for the sample size, which means it should be bigger than z sub alpha over 2 times the standard deviation over your margin for error that you are picking. And you're going to square that. So the squaring, again, has a potential of making this really big, especially if you're dividing by a margin for error that's close to 0. It's best not to ask for margins of error close to 0, because dividing by 0 can have huge results, or dividing by nearly zero values can have huge results. So you can only ask so much. Margins of error will always be there. You can't make it go away. Okay, so on that last problem, we got about a 2. Margin of error is 1.96, so it's about 2, and they're going to ask us to get it down to 1 point. Okay, and so there'll be this is going to be a penalty, right? Okay, but let's just summarize what we've got here. The sample size, let's say, I'm sorry, I'm going to change this. If we want to choose a margin of error, then we should sample at least n equals z alpha over 2 times sigma over the margin for error. And then you square that. A couple of comments. First, you're not going to know the population standard deviation, so use a sample standard deviation S to estimate sigma. So that means you're going to have to do a pilot study. You're basically going to have to gather data, maybe do 100 people again, and then you get a standard deviation from the 100 scores, and you would just use that here, plug it in, and then it'll tell you how many more people you have to survey. So I'm going to treat this initial problem with 250 students. I'm going to treat that as a pilot study before I expand to a larger study. So use a sample standard deviation S to estimate sigma, which is the population standard deviation. And so we're just going to pretend that's our standard deviation up above. So here they want to keep 90. Oh, they're changing the confidence level. Okay, so with alpha would be 1 minus 0.98. So this time it's going to be 0.02. And let's just use table A2 this time. So with table A2, your alpha is 0.02. Make sure you do 2 tails, which basically divides alpha by 2 for each tail. Okay, degrees of freedom just go down to large where the z-scores are. 0.02 two-tail. And let me bring that up here. Okay, so I'm going to zoom out and then I'll highlight. So the 0.02 is the second column of this table under two tails. So I'll just highlight that second column and then I'll zoom in on the answer. Okay, so again, 0.02 is my alpha, two tails all the way down, and it says 2.326 there. Okay, any questions about that? Okay, so I think we can fill this in then. So down here it was 2.326. So that's our Z alpha over 2. So again, the alpha over 2 part is the two tails part. You're splitting the alpha among two tails. Later on, we'll do one-tailed applications, but right now we're just doing two tails. All right, so then I think we've got everything. The margin of error is 1. Okay, so that 1 right there is our E value. We're picking a margin for error, but then we have to kind of release the sample size and do what this says. So our sample size is going to be the ZF over 2, which is 2.326, multiplied by the standard deviations. Well, let me put the formula down real quick here before I go this far. So it's Z alpha over 2 times sigma, whatever standard deviation you've got, over your margin for error that you're picking. Okay. And then you square that. So this is going to be 2.326. Sigma was, I don't remember, is 12. And then the margin of error is just straightforward. It's 1. And then we square that. Okay, so that looks pretty easy. Let's see. Just shout it out, you guys, when you get it.
$779.08.
Yeah, okay, so 779.08. Now, again, the key words here are at least up here. And so at least does not mean 779. It means this number or higher. And again, I'm not that neurotic where I think it's going to, 0.08 is going to make a big difference. I don't. But let's follow the rule and do 780. Okay, because you have to round up to a larger number. Okay, and that's the note, and the other note that I was going to add to the comment that I put up above. So I'll do this in blue, I guess. So up here, let's say and round up. Okay. And all of this is sort of, nothing is exact in statistics, right? So you're going to say a 1 point margin of error and it'll be approximately 1 point. It's not going to come out exactly 1. Okay, remember, it's all based on probability, which means all of this is just educated guessing.
Just to be clear in my head, the margin of error of 1 means that our interval will be plus or minus 1%.
Right. So now, and of course, you're going to expand your sample size. So the mean is going to change. And we've had discussions like this before. The mean was 76.5 originally. that will change when you expand to 780 people now from the original 250. And what will happen is that mean will get closer to the true population mean because you're increasing your sample size. So as this mean changes, your margin of error goes down with it. But if it didn't change, it will. But if it didn't, then you'd say, well, now I think the population mean is between 75.5 and 77.5. But you can't say that because the mean will change. Okay, so you know, this part here, you can't count on that. All you'll be able to count on is a 1 point margin for error. But you've got to sample way more people, basically 3 times as many people. And if again, you should think about the costs. I mean, what we had was only 250 is kind of a nice number. It's not too many. And now we're saying you've got to triple that to get up to 780, more than triple. And you're going from what was, let's see, the margin of error before was 2 points, 1.96. And now you're getting it down to 1 point.
You also reduced your confidence by 1%.
Oh, yes. Good call there. Thank you. So even with a lower level of confidence, the price is pretty steep. And yeah, it would get a lot steeper. If I had stuck with 99% confidence, you might remember this was a 2.576 before. So then it just gets bigger with more confidence. Again, more confidence means you have to allow more margin for error. So, but 98 is still really high. So I think we're good. And what time is it? It's 11:37. So that's it for the day. And we'll finish this. There's only one section left of this chapter. And just to let you guys know, chapter 7 is published in modules on Canvas. So before next Friday, if you're using printouts of these, then do get a printout of the module 8, or sorry, the module 7, I'm sorry, chapter 7 notes. And that's what we'll start with right at the beginning of class next time. Sorry, after we cover 6.6, we'll start into that. Okay, and it'll actually be super quick. All right, does anybody have any questions before we quit? Okay, guys, well then it's been great working with you, and I will have, I'm going to have your progress reports available over the weekend, and all that will be is just me looking at all your scores, finalizing everything, and then what I'll do is I'll also drop your low score, and I'll give you an average with both the scores, and also an average with only with the dropped low score. And this is just for your own kind of something to think about. In the end, I don't know which score will be dropped because there's still another test ahead. So, you know, it's all very hypothetical at this point, but it's just to kind of give you a sense of your standing in the class. And, you know, there's no looming drop date coming. You can drop all the way basically until finals week, I think. And they call it an excused withdrawal, right? So the penalties are not really high if you stay, and I would encourage you to stay if you think you can pass. But just let me know if you have questions, and I hope you all have a great week, and I will see you next Friday, and keep an eye open for that progress report. If you have any questions about it, ask me on Monday or one of my office hours, Monday or Wednesday. Okay, any questions?
Are you going to have office hours today?
Yeah, immediately. Yeah,
okay.
I got 5 minutes and I'll start that office hour for sure.
Your guy just got confused. Okay.
Okay, yep. All right, I'll see you guys. Anybody else? Okay, take care, everybody.
Bye. Thank you.
Bye.
Bye. See you in the office hours.
Yep, take care, everybody. Now, there's just one more topic here, which just deals with the fast. We're going to redo this lesson. Let's see if we can do it real quick here, just with a couple more confidence intervals. The only thing that happens here is that you don't know the population standard deviation. You have to use a sample standard deviation. And sample standard deviations vary from sample to sample. And sometimes they're bigger than they need to be, and sometimes they're smaller than they need to be. And we don't, if your standard deviation from a sample comes out too small, then your margin, you just have to look at the formula for the margin of error up here. It's this one. If the standard deviation that you get from a sample comes out too small, then your margin of error is going to come out too small. It's a real, you know, if it's coming from a statistic, it's going to vary. So if your margin of error comes out too small, then you're not going to be right 95% of the time, like you're saying. The problem of the standard deviation coming out possibly too small and the margin of error coming out too small means we're going to have to correct for that problem. So it's a little theoretical. You're not going to be tested on the theory. Okay, so we're looking at section 6.6. This is on confidence intervals for a population mean where the population standard deviation is unknown. Let's begin. We've learned to compute a confidence interval for a population mean, mu, when the population standard deviation is known. When the population standard deviation is unknown, we have a problem. In this lesson, we will solve that problem. So to compute z-scores of sample means, we use this formula. The z-score of a sample mean, you would take the sample mean and subtract the mean of sample means. Oops, the mean of sample means, which is the mean of the population. Okay. Divide by the standard deviation, or also called the standard error of the sample means. Okay. Now to step back, we know that the mean of sample means is the mean of the population you're sampling from, and the standard error of sample means is the population's standard deviation over the square root of the sample size, and that's what we're using to compute the margin of error down there. This formula has one variable that changes from sample to sample, so one variable that changes from sample to sample, and that's the sample mean. X bar is the only thing that changes when you change your sample. It's a given sample size. As this varies, the z-score varies according to the standard normal distribution. Which we've drawn many times. It's the bell curve of z-scores that is a little special because the mean is 0 for z-scores and the standard deviation is 1. That's only when you take the z-scores, okay? If we don't know the population standard deviation, then you can't do that computation. So we have to estimate it with a sample standard deviation. So this z-score for standardizing, so that you can use the standardized or the standard normal distribution, that computation cannot be done for standardizing to the standard normal distribution. Because the population standard deviation here in the denominator, that thing is not known. Okay, and I'm wiggling it around. It doesn't, you don't know its value. So instead, you have to use the sample standard deviation. So S is the symbol for the sample standard deviation. Okay. That's what we use in practice. Now, here's the problem. Before, the formula had one variable, okay? The formula now has two variables, okay? X bar varies from sample to sample, and S varies from sample to sample. There's two things varying there, and now the possible outcomes for the statistic are more variable. You get more outcomes. Two varying values in the formula causes additional variability. How does this affect the distribution of the above statistic? The distribution of possible values gets wider. So the standard deviation is larger. I'll say is greater than 1, which means it's not a normal distribution. Okay? So down below it says the additional variability is caused by the sample standard deviation. The variability in the sample standard deviation depends on the number of deviations from the mean that are random. How many deviations in a standard deviation are random? Ugh. Now I'm going to have to go back. So I'm going way back to chapter 2. I think it's 2.6. Nope, 2.5. Still in this handout. Okay, so here's 2.5. It's not 2.5. Where is it? Ah, here we go. Where we were doing the standard deviation. Okay, here we go. We started by averaging deviations from the mean when we were trying to develop standard deviation. So we had values and we had a mean, and we were trying to figure out how much every value deviates from the mean. And one of the things we learned is that when you add up the deviations from the mean, they always add up to 0. Okay. And here there were 12 values and 12 deviations from the mean, but because they always add up to 0, the last one always has to be the number that makes the total 0. So while there are 12 values, only 11 of them are random. So we say they're n values, but n minus 1 of them are random, and those are called the degrees of freedom. Okay, so going back to our lesson, it says, how many deviations in a standard deviation are random? Well, there are n deviations. Oops. Okay, n minus 1 are random. Those are the degrees of freedom. Now let me put that down below. So n minus 1 is the degrees of freedom, okay, which we usually just say df. Okay, the distribution of that statistic varies according to what family of distribution. It's called student's t-distribution. Student is the name of the guy who invented it. It wasn't really his name, it was his pseudonym, student's t-distribution. Okay. Why student? It's named after William Gossett. Studied yeast. For who studies yeast? Well, bread makers and beer makers for Guinness Brewery. In the early 1900s, I'm just making beer. Invented it but published under this pseudonym. How do you spell pseudonym? Pseudonym, I hope. Student. The company, it's just one of those things, when you do work for a company, they own your work, and they didn't want him taking credit for it, even though he did it, they owned it. Not unusual today, still. Okay, any questions? So that's students' T distribution, and I should say, the variability in the standard deviation depends on degrees of freedom. The less the degrees of freedom, the more the variability, because your statistics are less reliable and you have smaller sample sizes. So you see, when the degrees of freedom are really low, the T-curve has a low middle and heavy tails out here, just because it's more probable that you get wide variability with small sample sizes and low degrees of freedom. So the degrees of freedom indicate the width of the distribution, but do notice that as degrees of freedom increase, the T distribution is approaching the normal distribution, which is the highest one there, where its most probable value, the more probable values are in the middle. For the normal curve, they get pushed a little bit outward with the T distributions because of that added variability. So down below it says, as the degrees of freedom increases, the T distribution approaches the normal distribution. The margin of error in a sample mean when sigma is known is E equals Z alpha over 2 times sigma over the square root of n. We've already done that with a confidence interval. If sigma is unknown, instead of using the Z distribution to get critical values, we're going to use T alpha over 2. And we're having to use a sample standard deviation and divide by the square root of the sample size. So it's really the same computation. But you're going to get your critical T alpha over 2 instead of Z alpha over 2. I'm using a sample standard deviation now. You still have the level of confidence here in the middle of the distribution. Okay. Alpha is still 1 minus the confidence level. Okay. And alpha over 2 is the area of the tails, and then your critical values are called T alpha over 2. Okay, and it's just the number of standard errors that you have to go out to capture, 95% of the population or 99% of the population. And those ones that are captured, those means that are captured by that will be within the margin of error of the population mean. Okay, so we can go ahead and just do examples now. All right, so go ahead, the gather and check. It's the same rules. You still need the sample means come from a normal distribution. So we need for n to be, this is the check. Okay, we need to check that n is greater than 30 or the population is normal. You'll need your X bar value, you'll need S, you'll need N, and you'll need the level of confidence. And then don't forget alpha is 1 minus the confidence level. Okay. Your lookup is going to be T alpha over 2 now, not Z alpha over 2. Okay, and it's still table A2, where in the degrees of freedom column, you now know that that needs to be your sample size minus 1. you still go alpha 2 tails and down like this to the value which we will now refer to as T alpha over 2. So you're not going to the bottom row of that table anymore, where the z-scores are. Maximum error is easy now. It's E equals T alpha over 2 times S over the square root of n. So it's very similar to what we did before. The endpoints of the confidence interval are just x bar minus the margin of error, less than mu, less than x bar plus the margin of error. Like that. And the interpretation is identical as before. We had said we are a blank percent confident that the mean of something is between two numbers. Blank and blank. Okay, so it's super easy. And honestly, you'll feel like you're doing the same thing as the last lesson. Okay, so let's just do one real quick. It says the mean sleep hours for 35 students. Okay, these are statistics students. N is 35. This is bigger than 30. That's our rule, so we put the check mark down. We have tracked. X bar is 6.4. That's the mean hours of sleep for statistics students, and that's that. And the sample standard deviation, it says that these students, these 35 students, have a standard deviation of 1.6. That's from them. This is a sample, so this is the sample standard deviation that I'm putting down. The confidence level is 0.96, so my alpha is 0.04. Okay, 1 minus 0.96. Now we can go to table A2. Now we use degrees of freedom because we are using S instead of sigma. Degrees of freedom are n minus 1, which will now be 34. Remember, n is 35. Look up alpha equals 0.04. Make sure it's 2 tails. Okay. 34 degrees of freedom, which measures how variable the sample standard deviation is and takes that into account for the margin of error. Okay, I'm going to pop over real quick 34 and 0.04. Here's table A2. Clear it up a little. Okay, so going to 34 degrees of freedom, way down here at the bottom, and make my mark with that, I think. Okay, so 34 degrees of freedom, 0.04, 2 tails. This guy? I hope. So I see, let me double check it, but that's a 2.136. And again, 0.04, 2 tail, 2.136. Good, you guys, good job. So that's just straight from the table, straight look up. 2.136. Okay, and now the margin of error. It's just T alpha over 2 times S over the square root of n. So that's the 2.136 times 1.6 over the square root of 35, I think. So I'm hoping you got what I got, 0.5 7. I'm going to do 2 places because the mean has 1 place. So 0.58 really. 0.58. Okay. And now just confidence interval. So X bar minus E less than mu less than X bar plus E. Okay. So when you subtract X bar, that's 6.4 minus the error, which we're giving a 0.58. So on the low end, I'm getting 5.82. Less than mu, and now adding X bar again is 6.4. And you're doing plus 0.58, which is 6.98. And these are hours of statistics students at MassSAC. So we are 96% confident, assuming it's a random sample. It says it is. So we are 96%. Nobody's going to do 96%. They'll do 95. But we're just, it helps us learn how to use these tables. So we are 96% confident that the mean hours of sleep for what population? Well, Mount SAC stats students is between what do they say? 5.82 and 6.98 hours. It's too precise, but we'll leave it for here. And it's 11:35. Let's do another one. I think we can. 5 minutes. Let's go. Okay, and that'll finish it for the day. So on this one, it says we got 51 women. Fine. N is 51, which is bigger than 30. So check mark. Okay. The mean weekly salary is $726. All right, that's X bar equals 726. Okay. With the sample standard deviation, it says sample. S equals $185. 185. I like it when everything's a whole number. Now it says give a 95% confidence interval. All right, so the confidence is 0.95. So alpha is 0.05. Okay. Table A2. So degrees of freedom. You're going to go down to 50. How convenient. N minus 1 is 50. I think it used to say, I think it used to be 49 and they changed it so that it would be on the table. Just pick the closest. If you don't see your degrees of freedom, just pick the closest one. The alpha is 0.05 two-tail. Okay. And if you go down to that, ooh, J-Zarco, 2.136. I'm going to prove he's right. Okay, so 50.05, oops, 0.05 two-tails, if I can find it. That was way down there. Oh, wait a minute. Did I screw up? That 0.05 two-tail. I didn't get what you got. Maybe that's an old one. That's probably old. Agreed, 2.009. Maybe that other one was from the last one. 2.009 with a 0.05 two-tail. Okay, fine. So this guy is 2.009. Then our margin of error is t alpha over 2 times s over the square root of n. Let's put in the numbers. That would be 2.009. Yep, 2 standard errors in the margin of error. S is 185. And that's over the square root of 51. Okay. Okay, checking everything. Looks like 52 point, I'm just gonna say 52.0 because I'm gonna do one more place. 52.0. So when we do x bar minus e less than mu less than x bar plus e. So you're just gonna do x bar was 726. 726 minus 52. So that's 674, I'm going to say 674.0. Less than mu, less than, and we add them. It's 778. 778.0. I'll just, it's 0.0, I'll just refer to dollars now. I'll say we are 95% confident. That the mean weekly salary for US women is between 674, I'll just say 674. No point in saying 0.0. You could say and 0 cents, but what's the point of that? So between 674 and 778. Okay, and that's it. 11:40 exactly. All right, you guys. Got my office hour in 5 minutes, so feel free to join me, and I'll be talking to you. Take care. And my office hour is in a different Zoom meeting, you may remember. Jay Zarko, I think you should include units. Remember, you're trying to explain this to people, so, I mean, obviously dollars on this one, but yeah, I think you should include units.
Professor?
Yes.
When do we take next exam?
Well, it's on the schedule. So let me get this real quick. I have to go over to Canvas and I'll just read it to you so that I'm not going to drag you over there. It's on the syllabus also. So for this class, the syllabus says May 22nd. So that's a ways off. Is that all right?
Okay, thank you.
All right, take care.